please let me some announcement. 画面切り替わりますか。So, okay. As I said yesterday, so please fill out the form for accommodation survey. Please. So because of financial reason, so we need your cooperation. So this is a very simple form. Just you should input your name and what hotel you stay. So please for the financial support. So this is very important. So after this first session, so I'll send you all by email attached with this URL. So please access to this URL and fill out the form. And tomorrow, so we prepare the excursion tour in English and Japanese. 日本人の方も参加して OK です。So you can find a very beautiful classic city in the excursion tour. So if you hope to join to the excursion, so we have a registration desk for excursion at the symposium at the next of symposium registration desk. So please come to the registration desk and please apply for excursion program. So the deadline of application is 12:30. Today 12:30. So excursion application will be closed. So please come to registration desk in the morning. Okay, now it's time to start the first session. So 画面を切り替えてもらっていいですか？ Okay, please proceed, Chairman.
Yes, good morning, everyone. So this morning session we start with a presentation of the LUPEX, the JAXA mission to the moon, and will be given by Dai Aso, project manager of LUPEX.
Okay, thank you, Chairman. I am Dai Aso, LUPEX project manager from the JAXA LUPEX project team. Today I will introduce the LUPEX mission itself and our concept, our plan for beyond LUPEX. So the first one, this chart shows us JAXA's space exploration scenario, and the middle line shows moon exploration plan, and these are three contents on the moon exploration scenario. And the first one, landing technology. The second one, surface exploration technology. And also, we are focusing on science on the moon surface. And LUPEX is located here. It's the first mission for the space surface exploration technology. So what LUPEX is? The LUPEX polar exploration mission, it is in situ observatory of water ice in the South Pole regions. And our main goal or objectives is investigate the quality of the water ice. I will explain later what the quality is, and the quantity also. And also we investigating the resource, the support feasibility assessment to support feasibility assessment to use the water as a resource for the sustainable human activities on the moon. And this LUPEX is a joint mission with ISRO, Indian Space Research Organization, and ISRO will provide the lander here, depicted here, and science instruments. And also NASA and ESA will provide the science instruments to the rover. And this is LUPEX project objectives. The ISRO has some objectives, and the JAXA also several objectives. And the common objectives is for resource prospecting, and to investigate the quantity and the distribution of water ice on the moon, and we will obtain the data on states and the forms of water. And also JAXA has technology objectives to demonstrate the technology of lunar surface mobility, and also long duration stays, that means survivability for overnight stay for future lunar base construction. And this is the responsibility between international partners. And JAXA will provide the launch vehicle and rover and several mission instruments. And ISRO will provide the lander and some, for example, a GPR, ground penetrating radar, and mid-infrared imaging spectrometer. And NASA will provide the neutron spectrometer. I guess that it is very similar to the neutron spectrometer which will be installed in Viper. And also ESA will provide the EMSL, exospheric mass spectrometer for LUPEX. So this is chart shows rover path planning, just example, because we have not decided yet landing site. But this is just an example. We will land some landing point in the South Polar regions, and this is a landing site. And this color shows illumination ratio. So the yellow one is a very high ratio of the illumination ratio, and the blue one is a low ratio. So this is the landing site, and we will conduct the reference observation near the landing site. We can obtain the solar power using the solar panel around here, and traveling to waypoint 1, near waypoint 1, about 180 meters, and we conduct the full battery charging here, the white point. And this red point is waypoint 1. Waypoint 1 and waypoint 3 are the very small permanent shadow regions. And before we go down to the permanent shadow areas, we will perform the battery full charge at charging point. And we know that 10 to 20 degree inclination to descend. And we conduct the investigation of the water ice. Then we climb up the hill. The distance between waypoint 1 and waypoint 2 is about 490 meters. So you can imagine that how distance we will travel. So again, LUPEX will conduct the coarse observation and fine observation. So using those instruments, we will find any suspicious or potential area to find water ice in the ground, under the ground. So this waypoint is about 30 meter and 30 meter square, and we will decide the drilling point. Then we will conduct a fine observation using our drill down to 1.5 meter and heat the sample to remove the water ice from the regolith. So the LUPEX competitiveness is, there are four. The first one is direct measurement of water content, because we use the regolith itself to find the water ice. And second one is the high precision vertical sampling, because our sampler is located on the tip on the drill. So we can collect the regolith in a very high precision. So third one is mobility. The mobility is a very important to go to the variety of the condition of the environments. So very bottom of the crater or the very high mountain and so on. So mobility is a very important one, and our mobility is a very unique one. And the last one is overnight survivability, because there is a very good technology in lithium-ion batteries in Japan. So we use a very high performance lithium-ion battery and also a solar panel. So this is LUPEX technology application to the future missions. So the technology we will acquire through the LUPEX mission, this technology will be applied to pressurized rover or water resources plant, and establish the lunar bases and so on. So I will focus on technology application to the pressurized rover. So this is a technology field and technology item. Technology field, for example, such as sampling and energy and mobility and excavation. And we will use those technology in the LUPEX. And also we listed up the technology which we need for a pressurized rover. And of course, there are a gap between the LUPEX and the pressurized rover. So now we are investigating how we can improve the LUPEX technology to pressurized rover. For example, the overnight technology and also traveling one, and guidance and navigation control. We will improve. We will have to improve the LUPEX technology to apply those technology into a pressurized rover. So LUPEX output, we will make a 3D map of water ice and so on. So this is a concept of propellant plant. And for propellant plant designing, we will demonstrate the excavation technology, collection, extraction from the samples, and liquefaction and storage, and also fuel loading to the rocket, ascending units from the lunar surface. So our data can help the excavation designing, such as where to dig and how deep and how much quantity we have to collect the sample, and so on. And also extraction, our outputs can help the extract method and so on. So our outputs can be utilized to design the propellant plant. And the last one I have is LUPEX outcome. So there are many fields to build the moon base. For example, building to build the the facilities, and also create the energy and explore on the lunar surface, and also live in the lunar surface. And we think that joint research activities with our industries or academia in technologies for sustainable human activities on the moon is mandatory. So we already start with joint activities with many companies and universities for investigating to design the lunar bases. Okay, thank you very much. And this is just Twitter, I mean X account for the LUPEX, and also you can find the LUPEX information in the LUPEX website. Thank you very much for attention.
Thank you very much. I think it was a very, very interesting presentation explaining how LUPEX helps preparing the utilization of water on the moon. We are a little bit behind schedule, so I suggest that we move on to the next presentation. That will be about living and driving on the lunar surface, also by JAXA, by Fumiya Tsutsui from JAXA. It's okay. Okay. So due to technical IT problems, we move on to we take the next presentation first. So that's science objectives of the Tsukimi lunar mission given by Hidemi Miyamoto from Tokyo University. Thank you.
Talk instead of me. Yeah, hi. Thank you, Chairman. My name is Hardy Miyamoto from University of Tokyo. I'm talking about this Tsukimi mission, which stands for the terahertz surveyor for kilometer scale mapping. I know it's asking a little too much, but Tsukimi means kind of moon gazing in Japanese, so it's a little bit important for us. And this is not a JAXA mission. This is funded by Internal Affairs of Communications, so it's a little bit different. But of course, we collaborate with JAXA. So this mission is using the terahertz instruments. So let me speak something about the terahertz. The terahertz band remained largely unexplored. So there are, of course, lots of very, very good, great, intense previous missions to observe the moon. They use a lot of different wavelengths. Like I put the x-axis as the frequency, and some of the major ones shown, such as like LRO, Chang'e, and Chandrayaan, and Kaguya Lunar Prospector, something like that. And then we found that the telehealth region remained unexplored. So, but the reason is this wave band is a little bit difficult technologically, but recently technology advanced, so it's available to observe the moon in this region. So the Tsukimi mission will use this frequency band. Similar observations have been made by Chang'e MRM and LRO Diviner. So this mission will be complementary to the existing data already available. The Tsukimi spacecraft is a very, very small satellite. It's only 80 centimeter size, 100 kilogram in mass. The instrument itself is a simple successor of the SMILES mission, which is an onboard instrument of International Space Station. The Tsukimi spacecraft is scheduled to be launched in fiscal year 2027, and we plan a 1-year operation duration. We'll measure the brightness temperature of the moon in the terahertz range and map the heterogeneity of the lunar surface, soil in terms of thermal diffusivity and apparent permittivity. We consider this terahertz band can be very, very useful to observe the sweet spot for future resource utilization because the nature of this terahertz band, we cannot look deep. The sensitivity at depth depends on the frequency, of course. We use only like a 490 gigahertz and 280 gigahertz band, which penetrate only up to at most 30 centimeters, typically several centimeters to like 20 of the centimeters. So we only look at uppermost 30 centimeters, that's it. But we think that this might be important because I don't need to mention about this, but as everybody knows, the LEND, MEMCube, LoRa, several other instruments indicate that water or some volatile may exist in the cold regions such as PSA in the South Polar region. But the model calculation, something like this, to understand the temperature profile on the surface indicate that the maximum temperature probably stays at the kind of lower subsurface. So if we have the volatile material, it should remain in cold temperature. So we feel that the highest temperature experience should be lowest. It's kind of complicated, but the point is like this portion is should have achieved the temperature variation, but the highest temperature stays lowest for the long period, which means this depth can be the best candidate for finding the volatile. So we prefer to go to look at the shallow depth region. Another reason is the 30 centimeter may be accessible a lot better than other depths. Just using the ordinary machines can work to access the 30 centimeter depth. Also, for the material, up to 30 centimeter can be efficiently collected. So we feel we're not 100% for sure, but probably most energy effective per unit volume. The point is, of course, it is highly dependent on the model, but the general model indicates that the deeper excavation depths require higher energy cost, of course. But at the same time, shallow excavation depths require longer lengths to carry if you try to collect the same amount. So the balance is very important. At least from our calculation, the cutting up to 30 centimeters could be the most energy efficient. So we prefer to look at only 30 centimeter in depth. This is the Tsukimi data pipeline and its product. So I will just skip the detail, but we will observe at terahertz band, and then we make this RPR map, which represents the relative polarization ratio. Then we get the apparent permittivity map, which is called the, apparent bulk permittivity map. Also, we get the brightness temperature map, which can be converted to the thermal diffusivity map. And combining these two, the electricity and permittivity map, we may get, we may determine the promising area with resources. Just let me note that, of course, this permittivity or the electricity, anyways, do not thoroughly constrain the chemical composition, but we have length data, and M-cube data, Kaguya data, so we can compare. Also, at least some relative change in permittivity can be obtained, which will be useful to identify potentially useful materials such as volatile and metals. And in fact, we also developed, this is different from Tsukimi mission, but we are developing this new instrument, which is called LDA, Lunar Dielectric Analyzer. It's a TRL6 right now, and so it's ready to deliver. If any of you guys have some mission to the surface of the moon, we want to provide it to your mission. And if it goes to the surface of the moon, that's great, because it will measure the electricity on the surface of the moon for the first time. You can measure the electricity. If you bring the sample back to Earth, you can do that. But under the terrestrial gravity, the value can be totally different. We need the in situ data to really understand the nature of the MRM or Minisar, Diviner, Mini-RF, or the Tsukimi data. So we need really the ground truth data on the surface of the moon. So we are ready to deliver. Just let me know if you have some chance to bring something to the surface of the moon. And of course, JAXA's LUPEX mission, it will bring the GPR. So it provides certain important aspects, but still, I feel the real value of permittivity is needed. Anyway, if we get the data from this kind of instrument, we get the real in situ data, permittivity data for different variations. So we can compare these, the result of these different but similar observation. As I said, like the bandwidth of each instrument used are different. So these are all complementary. Okay, this is a summary. I don't know if I still have time. Or maybe I have. All right, thanks. So just let me say again, like this Tsukimi mission is, again, terahertz surveyor for the lunar resource mission scheduled to be launched in 2027. And the Tsukimi measured the brightness temperature of the moon in the terahertz range, and map the heterogeneity of the lunar surface soil in terms of thermal diffusivity and apparent permittivity. Again, the permittivity values do not thoroughly constrain the chemical or mineralogical composition of the surface of materials, but relative changes will be essential to identifying the candidate site for the future resource utilization. The resulting permittivity map may be particularly important compared with in situ observation data by landers, rovers such as LUPEX, and potentially some other agencies or commercial missions. That's all. Thanks.
Thank you very much. I think we have time for one question.
So you mentioned that you mostly measure permittivity, but for instance, this range, sub-millimeter, is very affected on Earth by water absorption. So would you be able also to detect some absorption due to water ice that is mixed in the soil?
Actually, that is within the scope, of course. So if the soil absorbs or have some ice content inside between the soil part, the porosity, then it will increase the dielectricity at least like we calculate 0.2 will be increased for the 5 weight percent of water ice. So and we have the precision of about 0.1 or less. So we can identify maybe 2 or 3 weight percent of ice effects. But we cannot say this is ice. We only say there is variation. Thanks for the good question.
One more question.
Good question. You mentioned the terahertz range is useful to compare with microwave from LRO, for example, or
Right.
higher wavelength.
Yes.
Can you explain more how the combination of those measurements can be
Yeah.
more precise, and if those measurements have to be taken at the same time, or if they're taken years apart, is it still?
Right, thanks. That's a very essential question. I have 2 reasons. One is the penetration depth. If you change the wavelength, longer wavelength, it penetrates longer, and the shallow, high frequency, it goes shallower. So we have shallow data and the deeper data. So we need some middle data, which is the reason we selected terahertz. Another reason is the electricity or permittivity probably depend on temperature. Of course, it depends on the chemistry or the packing density. But importantly, it can depend on temperature, and the temperature variation can affect the observational data, except for the terahertz region. We are not 100% sure. I mean, theoretically, it probably in terahertz region, the temperature doesn't really change the permittivity. But we are now working on terrestrial, laboratory experiments to confirm this is true or not. But at least from theory, that's a standard theory. The permittivity doesn't depend in terahertz region in temperature.
Okay, thank you very much.
Thanks.
Very interesting.
Thank you.
So now I just want to see if we go back to the previous one. Okay, so now we have the presentation on living and driving on the lunar surface by Fumiya Tsutsui from JAXA.
Okay. All right. Sorry. Thank you, Chairman. And I'm Fumiya Tsutsui of JAXA, Human Space Flight Technology Directorate. Then, JAXA has formed the organization to very focused on the development of pressurized rover, and now from the December 1st and November 1st. Then we started our study for the pressurized rover now. Today, I will pitch you some brief pitch about the concept of the pressurized rover to be a part of Artemis mission. Okay, pressurized rover enables our exploration on the lunar surface out to very extended area because the pressure cabin for crew living in short sleep for a few weeks inside, and we will provide the mobility for longer range traverse for more than 20 kilometers a day. Then we will provide more larger range of exploration. Then the objectives of the pressurized rover is our Japan's major participation in the Artemis mission. That is a first big asset on the lunar surface. It could be. And also, we are going to expand lunar human activity on the lunar surface. That is a real thing to be done. And also, we're going to demonstrate our technology for exploration on Mars. That is, we can demonstrate our technology or design feature, design methodology of the on the mobility for the sub-Z environment. And also we will provide the science for longer and greater range. Then the mission concept is we're going to launch in this decade. This is target for us, and we will operate for 10 years after that. And then first phase, we will focus on the South Pole region. But if the technology is getting matured, then we will expand our range to far away from the polar region. For every year, we will give you a month of crewed mission, and after rest of days per year is uncrewed. Provide the uncrewed robotics exploration with the robotics or a remote sensing. Then lower side, as I said, this rover will give you 20 kilometers up per day travel, and also as a total 10,000 kilometers of travel we're going to do. Then its mobility provide 20 degrees of max slope capability, as well as they get over to the obstacles of the 30 centimeters on flat surface. That is the capability of our mobility. Then now I will give you some information about the mission timeline. That is a reference for our design. And first, left-hand side, you can see the human lunar lander will get down to landing site of the lunar surface. Before that, the logistics lander will carry any cargo for the crew or any science instruments. And once the crew is landed, then the logistics will be carried into the pressurized rover. Then we will start the exploration. Then 2 weeks of exploration. Then we will have some lunar night days, some days. Then we will exchange the waste and logistics as well again, and we will repeat another 2 weeks exploration. Then after that, the crew will ascend to the gateway, return back to the gateway. That is a concept of the operations. For 2 weeks exploration for crewed mission, every day we will 8 hours. We will have 8 hours of traverse and EVA activity, and the rest of 16 hours we're parking on the place to charge batteries. Then we will repeat these things for 5 or 6 days. And we have 1 day off for crew. And also we will repeat that next week. Such kind of operation we expect for our design of the vehicle. For uncrewed mission, we need to have a longer lunar night period. We need to overcome the lunar night for longer, so we need more power to survive. So we will have 8 hours robotics exploration and traverse, and every 2 days we will have 8 hours of exploration, and the other 40 hours we will charge batteries. That is our concept of operation. Then exterior. Okay, you can see the any kinds of antenna or windows or cameras or like that. Also, backside we will have a gas tank or something, robotic arm for the robotic exploration. Interior side, forward side has, of course, driving seat for 2 crew, and on side we will have some logistics storage, or deck side has some equipment for this pressurized rover. And rear side we have a EBS suits stored, and yes, also we have a hatch to go out. Subsystems, we have many subsystems, but today I will give you some picture about the driving system and also some small short picture about the e-cruise. For the driving system, navigation and guidance will give us autonomous control of the rover. But for the early phase of operations or missions, we expect to have remote driving from Earth or crewed driving first. After the maturation, the technology matured, we will install the autonomous control of the rover as well. Okay. For any scenes shown, we do not know how feature the lunar surface has. We do not know exactly, so we expect many scenes for the rover need to overcome. So we will provide many control functions for those scenes. Rover is going to have 6 wheels. Then those 6 wheels have independent control, and those control will be dedicated for any controls. And then, for example, when we overcome climbing on the regolith, we need to control the traction control for using 6-wheel control. Also, the lighting conditions. This is a simulation of the lighting, and you cannot see left-hand side, cannot clearly see the obstacles, but you can find instantly now that big rock is there. Those obstacles are very hard to detect in this kind of dark environment because of the South Pole region. Sunlight is very low angle. So we are going to provide direct visual by window and also the cameras, but we need to have another methodology to detect objects like LiDAR. We're going to provide LiDAR to detect the objects from the 20-meter distance. Then I'm going to provide some information, like a screen monitor on the front inside of crew cabin. Then it is overlaid. Driving information will be overlaid on the screen monitor of the camera. That shows vehicle data and the obstacle information, and also route assumptions for crew to drive. Such kind of simulations we are doing now. Last thing is Eclipse. That is almost copy of the gateway I have Eclipse, and it will be sized down, downscaled, because gateway I have Eclipse has 4 crew members sizing, but it is 2 crew member sizing. So we're going to downsize the I have Eclipse for this applications. This is a situation of our, that is all from me and for today. And I would like you like to this pressurized rover to be realized in a very how to say, very soon. And I would like you stay focused on this pressurized rover. Thank you very much.
Thank you very much. I think we have time for one short question, and then we move on.
How do you think of the emergency system when the pressurized rover has collapse with the atmospheric pressure inside? Do you have a kind of a special Eclipse system to support the crew if you have an emergency system?
Any kind of emergency we need to think about the, for example, fire or depressurization or any others, then of course we need to think about. But actual methodology is to go back to the EVA suit, and then we will obstacle to the environment in that contingencies. That is our concept now. Okay.
Okay, thank you very much.
Yeah.
So now we move on to the next presentation on JAXA's Open Innovation Platform for the Future of Space Explorations. And I'm not sure who will present there. Funaki.
Thank you.
Thank you.
Okay, so good morning. I'm going to talk about JAXA's Open Innovation Platform for Future Exploration. My name is Iko Funaki of JAXA's Space Exploration Innovation Hub Center. And I quite appreciate we have a chance to talk about JAXA's missions as well as JAXA's research activities, which is I'm going to talk about. So this is a summary to today talk about our center, what we call TANSAX. TANSAX is JAXA's Open Innovation Hub Center for Future Space Exploration to invite Japanese industry and academia, in particular non-space community, into research and development for space exploration. TANSAX R&Ds cover not only near-future lunar missions, but also far-future lunar and Mars activities to ultimately enable permanent stay in these areas. And our joint R&D platform with funding introduced in this presentation to invite potential Japanese industry and to initiate international cooperation. So this is the outline. After talking about JAXA's activities on exploration and TANSAX law, I'm going to talk about research fields of TANSAX, highlight out so far from TANSAX activities before summarizing today's talk. So my colleagues, Aso-san and Tsui-san, talked about some future JAXA missions. Yesterday morning, Yamanaka-san, JAXA's Space Exploration Center, talked about a gateway mission, STREAM, and MMX. In addition to these future missions, we are, of course, working on study on broad lunar surface exploration in the future. And in that sentence, partnerships with industry as well as academia is quite important. So TANSAX tried to bridge the gap between current or existing or near future lunar projects and permanent activities on lunar surface. So in Japan, there are several research and development programs related to space exploration, such as Moonshot, Stardust, but TANSAX provides open innovation R&D platform for future space exploration and lunar activities. And the role of TANSAX and the approach of TANSAX is explained using this view graph. Our role is to create key technology for space exploration 10 to 20 years ahead with new industry partners and academia, and to invite new partners to R&Ds. TANSAX provides open innovation platform projects like this that provides funding for collaborative R&Ds between partners and JAXA, and it tries to obtain two objectives at the same time: new technology that can be used for future lunar missions, and new technology that can be used for the business on Earth. And it incorporates requests and seeds information from industry by using RFI and RFP approaches. And with these approaches, the partners can invest in their R&Ds since their activities directly lead to their businesses. So far, more than 170 R&D programs were conducted, and more than 200 entities joined this program, and 90% of which are from non-space sectors. So research fields of TANSAX so far are concentrated on these three categories: frontier exploration, production construction, and habitation. So in each research region or fields, several topics are provided, such as Lambda, robotics for future mission, new exploration ideas, scientific influence, and so on. For production and construction, ISRU, a remote and automated construction, or lightweight and efficient system in infrastructure. As for habitation, environment control and life support system, and residential modules, and lifelines, and so on. And for each categories, we have a variety of research partners and a variety of research output as are plotted like this. And some of them are for frontier exploration, such as robotics, and some of them are insight to resource utilization or construction, and some of them are habitation. And you can also see these categories, key devices and components. So there are very many key device and component developments related to these three categories. So from now on, or in the rest of my presentation, I'd like to talk about highlight output from TANSAX using some slides, maybe 5 or 6. So this is the first one, highlight output of high sensitive flash LiDAR. Flash LiDAR is a successful case of dual utilization, that is accelerating business on Earth and finding new application to space activities. So highly sensitive flash LiDAR can be or is expected as an image sensor for medical application, navigation for cars and drones. As well, it's applicable to flash LiDARs for HTVE, transport vehicle, new version. And also, it is expected as high speed and high reliability sensors for lunar lander. So you can use them for industry on Earth and exploration missions as well in space. So we call this case dual utilization. And second one is new robotics for space exploration. So in this case, for example, a transformable small robot level 2 or SRACU, baseball size, will be released for Japanese small lunar lander stream to explore the lunar surface. So this is another successful case of dual utilization, accelerating business models. They sell a quite interesting model, premium type toy model SRACU on Earth, and they find new exploration opportunities. So this is very small but fascinating space step for JAXA and non-space industry. So this figure shows SRACU's movement when he's released onto the surface of the lunar. So it automatically wakes up and start moving such operations to find his mother lander stream satellite. That will happen early next year. So another highlight output is production insight resource utilization. So ISRU is a versatile technology for sustainable lunar activity, and a variety of ISRU methods are pursued in this program, including finding water and using water on lunar surface. So we are pursuing lunar fuel plant concept by JAXA JSX, and example research outputs are something like this. You can see afterwards on the proceeding. As well, we also have a chance to cooperate with construction or housing businesses on Earth. So R&D toward efficient construction are conducted, such as development of lightweight or electric machines with Taguchi Industrial, development of automatic or remote construction technology with Kajima Corporation, and also a sustainable housing system that are easy to construct and easy to maintain. So this movie shows the last smart housing demonstration on Antarctic. They say they are going to simulate the harsh environment on lunar surface. I suppose it's quite different between an Arctic environment and lunar surface, but we can learn how we can easily manufacture these devices, how we can easily construct them, and we can get the know-how to operate in a harsh environment, they say. So they will lead to future lunar habitation modules. And at first, highlight output for habitation, efficient production of food, acres, and necessary infrastructure studied. For example, agriculture provide a package for making lettuce, minimizing water supply in the form of fog planting, and the liquefaction of food residues to reduce planting, and CO2 separation and storage for human to stay. So there are many topics we are working on with our partners. So I'd like to summarize my talk. I introduced JAXA's Space Exploration Innovation Hub Center's activities that provides unique opportunity to foster non-space industry to participate in the future lunar exploration. TANSAX will continue our R&D efforts with Japanese industry as introduced in this presentation. So future activity will focus on more specific architecture or subsystem to satisfy the growing demand on the lunar surface, and RFI, request for information, next version is soon issued from TANSAX in late December this month. I also wish TANSAX and TANSAX Japanese partners will actively interact with the activity in the Moon Bliss Association, because we are going for the same goal of sustainable lunar surface exploration. And thank you, and that's all.
Thank you very much. There's time for one short question.
So you showed many elements and R&D. So are you planning to have some prototype moon base with all the system from beginning to end, and would help us also to inform the design of future lunar base? Do you have a terrestrial version?
Oh, we are not planning a full demonstration of full architecture, but maybe he's my helper. So we are going to, we separately demonstrate. We divide them into subsystems and demonstrate them. So in the future, maybe we can demonstrate the full architecture on the lunar surface with a subscale model or a full-scale model. So we wish we are going to try that activities with you. Thank you.
Thank you very much. Big applause.
Thank you.
Okay, and this leads us to the last presentation that will be given by John Mankins on the Moon Village Association architecture study.
Yes. So good morning. The presentations this morning have been exceptionally interesting. I would like to share with you, if I may, very briefly, an overview of the architecture studies that are being conducted through the Moon Village Association Architecture Working Group. Firstly, announcing that at the 2019 MVA Workshop and Symposium in Tokyo, we announced this case study, OASIS 2045. And so today I am officially announcing that we are making an adjustment to the timeline for the case study to OASIS 2050. And so you will see crossed out everywhere 2045. Now we are 2050. So we all know very well the Moon Village Association. So this is just a generic slide. I won't spend any time on it. So what we did in this case study was to say, what would the first lunar settlement be like? And what we observed at the time, starting in 2018, 2019, is that there were many activities starting from today and then looking forward to plans for example, the Artemis sortie missions and the base camp and so on. And we looked forward to 2045, now 2050, to say what would a first human lunar settlement be like. And so we chose a location in 2019, just here on the lunar South Polar Ridge, presuming that a settlement, a permanent settlement, would be well to be located like the, not cave dwellings, but the dwellings in the cliffs in the American Southwest or in the Middle East, where the environments are rather harsh, and to dig into the side of a lunar crater. And to do so in this particular location was extremely attractive because from this spot you can see the Earth when it's in the right part of the orbit and the right time of the year. So the Earth rises. Each of those two craters are just below the ridge line where there is a great deal of sunlight. Each one is about 700 to 900 meters in diameter. And so the concept is to put the, and I won't spend a lot of time on the details of this. It's in past papers presented at the International Astronautical Congress, and it's on the MVA website. But to put those two, to put the settlement in the edge, like a cliff dweller, of those craters, and then to build out in the base of the crater and take advantage of the natural radiation protection and so on. These are also quite accessible to several of the locations like the Sputus PSR and Sverdrup and the Gerlach and so on. Several locations that are permanently shadowed regions and where water ice has been detected by past missions. And we also identified a location for a spaceport, which is on the far side of the ridge, only about 4 kilometers away, but providing significant physical protection without construction from the potential of blast effects during landing or some kind of an accident. So that's the general concept and the general region. I highlight just one other feature, and that's, if you don't think about it, it's easy to forget. The difference in elevation from these locations in the pale violet to these locations in the dark orange is thousands of meters. The elevation differences at the lunar South Pole are extremely severe, comparable, for example, to the Grand Canyon system here on the Earth. And the distances are on the order of tens of kilometers. And so, for example, going into Shackleton, you get slopes of like 40 degrees or more. And so it's very rough terrain and all really closely packed together. We were very gratified because this location was later chosen just on the edge of 2 of the Artemis prospective landing sites. But we chose it first. This is just a summary of all the different kinds of building blocks for the case study that have been identified in categories such as utilities, transportation and logistics, operations, and so on. And in this framework, just pressing ahead because of the limited time today, we have developed a functional modeling framework that provides an overview of the interrelationship among the building blocks in terms of key flows of information, energy, both power, thermal, and so on, and materials. And then going back from the ground through the transportation network into the surface settlement, the oasis, and then into specific mission and market functional areas. These are the major categories of the building blocks and the operations themes for identifying prospective markets within the context of the OASIS 2050 case study, things like government and scientific research services and commodities, government or operations services and commodities, and so on. And then we are framing these in a series of systems analysis studies to try to look consistently from the beginning to the end through specific use cases. I'm going to go forward to this one. On each of the kinds of services that might be provided to the customer classes that we talked about a moment ago. And the idea is to, and I think I can go back. No, yes, there. The idea is not just to look at it in a vacuum, pun intended, but rather to look at the interrelationships among these different elements of the lunar settlement and identify what are the actual requirements. So just to give you a specific example of one of these use cases, surface propellant for reusable lunar landers is a critical issue associated with a long-term settlement on the lunar surface. You can't throw away landers. And in order to have a reusable lunar lander, you have to have propellants. In order to have propellants, you have to have power. And so this is a specific case study that goes from the beginning in the regolith through the use case to the point of restarting the cycle where there is a propellant hauler system that provides the propellant to help the refueling of the reusable lunar lander. And then you back up into the point where you have the delivery of the LOX hydrogen. You back up to the point where you have the liquefaction and the purification of the LOX hydrogen, and so on, all the way back to the regolith. When you extract, you dig up the regolith and you extract and so on. This then feeds into a particular model that we have for the reusable lunar lander, which is a LOX hydrogen model that was developed a number of years ago by Yushnoi and presented at one of the past workshops. And so, for example, from this scenario, you discover that for a payload of 8 metric tons, a reusable lander with LOX hydrogen, that you require on the order of 1.5 megawatts of ongoing power if you're going to have a reusable lunar lander mission twice a month. And so this kind of analysis, this is not the final conclusion, but the point is this kind of analysis, and it's got all the various assumptions such as how much energy goes into the mining of the regolith, and so you can test that and see how much would it turn out to be with different kinds of mining systems and so on. But it allows you to extract from a high-level functional operational requirement, like landing 8 tons twice a month, to how much power do you need on the lunar surface for how much propellant, and then sort out all of the interim details as well. And this just then talks about another use case. So here you see the power requirement, the propellant requirement, and then the mining and construction requirements. A new thing that we are adding this year is science, i.e. we see that science as one of the principal market opportunities for a lunar settlement. So lunar settlements don't live by raw materials alone. They have to have a financial life. They have economic viability. And so that means they have to be able to sell things to somebody in order for there to be finances that are viable. So government and scientific research services and commodities includes, includes not only the power, the navigation, the transportation, and so on. It also includes prospective services and logistics for visitors who may be scientists from a particular country that want to come to the moon to do scientific research, but they don't have their own government end-to-end space program, but instead they pay for somebody to get them to lunar orbit. They pay for somebody to get them to the lunar surface. So this is a commercial town on the lunar surface with on the order of 100 population plus then the visitors coming and going. This is just an example of the kinds of high-level systems analysis modeling, and it's just intended to illustrate that for a particular set of assumptions that you can take a slice through this complicated trade space and determine with a finite set of assumptions and a high-level characterization of systems like the ice mining system, the water extraction system, the water electrolysis system, and so on, how much power for how many landers per year, or per month, if you have a certain set of input characteristics such as the water ice that's actually in the regolith that you're mining. And this, of course, is a variable to be determined. So just in closing, this is the vision of the OASIS 2045 with the settlement embedded into the edge of one of the craters, those 2 craters I mentioned earlier on the South Polar Lunar Ridge, mining activities taking place in the permanently shadowed regions, and a spaceport on the far side of the ridge. This just summarizes what I've just told you. There will be a number of upcoming opportunities to participate in Moon Village architecture activities, including an upcoming architecture workshop, which will be announced shortly, will take place after the first of the year, will be entirely online. The International Moon Day, which you've heard about already, and Nasser Al-Sahaf is still here. He's the chair of the International Moon Day group. And of course, next year there will be the 2024 Moon Village Association Workshop and Symposium, and we'll be making a major announcement about that at the end of today's session. So, thank you so much.
Thank you, John. There was 13 minutes and 20 seconds, so I think we can have one question, and then have a short break.
Oh, thank you. Very interesting talk. I have just one naive question. You mentioned about the Earth visibility for the selection of the location of the settlement. Why is it important? I mean, is it a technical or mental thing?
Absolutely psychological for the tourists. So one of the fundamental markets, there are several fundamental markets that are included in this case study. One of them, of course, there's the providing things for other people who are doing business on the moon, like transportation propellants. But then there are fundamental markets like infotainment, space travelers, tourists, and visitors. There's things like the scientific research and so on. Many of these have nothing to do with seeing the Earth, but if the transportation costs come down, as we believe they will with the reusable launch vehicles, nobody's going to go to the moon to sit in a hole in the ground and watch things on, on TV. So you're going to want to look out the window and see the Earth. And so fundamentally, if you're going to get somebody to pay $100 million to go to the moon, they need to be able to look out the window and see the Earth. And so it's a driver for that market.
Thank you very much. And that's it for this session. Thank you.
Thank you, Bob. So let us take a 10-minute break. The next session will start at 10:30. So please enjoy our exhibition and coffee break. So coffee is served in the exhibition hall. And if you want to join the excursion of tomorrow, so please apply it on the registration desk. The deadline of application to excursion is 12:30. So this break is one of the last chance to apply excursion.
そうだね。
Good morning, ladies and gentlemen. We are about to start. Please be seated. We are about to start. Good morning, ladies and gentlemen. My name is Satoru Cross of Yokohama Electric Corporation. I am the chair of the second session. Please be seated. Okay, so the first session of the second plenary talks is the layer project, New Life Spheres opened up by AI Robotics, presented by Munetaka Ueno Sensei. Ueno Sensei, floor is yours.
Yeah, Kurosan, arigatou gozaimasu. I'm talking about the research project, so not the developing project and not the business, so please relax this session. And the name of the layer is the name of the project of our moonshot project. And the name is after, just according to the old manner, this is one of the name of the Greek old history, is just the name of the mother of Zeus. And, but this is a project operated by Moonshot. This is a national project from the government. And not a JAXA project funded from the government directly. And we are operating this research project using the several institutes within the inside Japan, and you many times you see these types of illustration, but this is very rather concrete habitation module. But this is not the first step you can understand, because this is not so easy to realize instantaneously. So our habitation module is aiming to realize the first step on the lunar camp, just a very temporary shelter. So but the important point is that this is a very important step for the humanity, because the very first step towards the space habitation beyond the moon. But the first step must be realized by step. And also, we will use the AI and robotic technology together into the temporary habitation module. So it is called by robotic habitation, enhanced by AI. This is a very challenging program. And we are aiming to realize these types of aspiration, just like this. We are just developing these types of inflatable module and deployable structure and small robot and working together. And this is a very big step to just we will go out from our incubator Earth towards the space, and this must be a very big step for humanity, and also the challenge to our civilization itself, very important step for the humanity. And our plan is very important steps and achieving the portability in the extreme environment, just like a lunar surface. And this is very important. And we will realize these types of habitation module with the inflatable technology and also the deployable structure. And but if we put this temporary habitation module on the lunar surface, it is not a smooth terrain, but we have to consider about the unknown extreme environment. This is a very important point we are thinking. And so the survivability and adaptability is a very important issue for our research. And in this purpose, we are using the cyber physical system to capable the functioning unknown extreme environment, and also the robotization of the flexible structure itself. So in our research project, the habitation module itself is robotic. And also the realization of small robot just a cooperative with a larger habitation module, just like this. I will introduce to later. And collaboration is very highly important under the simulation inside the cyberspace. Okay. So the cyber physical system is a key issue in our project. So just achieving the system effectively operate in unknown environment. And also we can deploy or we can expand our inflatable module under unknown environment, just like this. But important point is a very cyclic learning system in the cyber physical system using the models, simulation, and data assimilation. And I will skip this slide. Maybe I will introduce later. And the uniqueness is the autonomous operation of the residential module itself, and also the coordinate of collection action through the connection of 3D transformer robot, and I will introduce later, and realization and very fine movement with a soft robot. We are just making the inflatable structure, but still this is very soft type robot and structure. And even on the soft surface, we will put another soft robotic arm from the very vinyl structure. But we can control this type of soft structure on the soft surface, very fine driving. After the cyclic simulation of AI, and also advanced robot-driven capability, and because you please consider just such as tube-type habitation module, the beginning of the inflation is very rather easy. But if you want to move these types of habitation module with cooperative small robots, but it still needs a large power to move these types of module. But if the module itself can transform a little bit to be very easily rotating, just like that, then these two cooperative working can realize some kind of moving, just like this. This is, we started this project this year, so we worked only a couple of months from the beginning, but this is an element of the one single small robot. This can catch another robotic module, and these types of operation, this can climb these types of larger module, and also these types of inflatable system. This is a very, very plot model of inflatable module, and the upper part shows some kind of in-sheets manufacturing of the vinyl system, and we can accumulate these types of system up to this soft robotic arm. And also we will use this atop the inflatable module just like this to work or check the surface by the camera atop of the softic robot. And this and those are all the projects in our research project. And the first step must be applied for the some ground uses, just application of these types of utilization. In some cases, disaster strike, just the shelter, inflatable shelter for the temporary uses. Or sometimes we will bring this to the depopulated region and very distant region or outdoor setting must be our first step for the application of our research goal. But the important point is co-evolution of the system from using the simulation inside the cyberspace. And all the structure must be modeled into the cyberspace, not only the inflatable module, but all the small robotics mechanism into the cyberspace, and will make a co-learning and co-evolution between the physical space and the cyberspace. So this is a very new approach of the cyber-physical system with a very complex systems. So, and this research project is supported by the national project Moonshot Research and Development Program. We are working in the Goal 3. Goal 3 means the co-evolution of human, AI, and robot technique. This is one of our project is one of these projects. And also we have milestone 2025 and 2030. And we will apply our proto model technology into the future lunar base constructions. And next page must be a team of our project. We have 5 sub-projects in my project. And one is operated by Tokyo University of Science, Professor Shinichi Kimura, just like this type of module. And the second sub-project is a deployable module using the origami technique, very Japanese-like technique. But realistic work is some co-group of Meiji University. And all cyberspace simulation and data assimilation was done by Sansoken in Japanese, just the National Institute of Advanced Industry. And also the total control system is developed by JAXA, our team. And small robotics module, just like DS types of robotics, was developed at Doshi University, Professor Watanabe, who developed the SoraQ also. And this is a very huge project. And not the development project, but and also the Moonshot project is a rather survivable project, and we have many gateways, stage gate, and the total, if we extend the project up to 8 years, we will go to the realistic application for the grant. Thank you very much.
Thank you very much, Ueno-sensei. Just one short question if you have. Any question? Okay then, thank you very much, Ueno-sensei. Thank you very much. Okay, next presentation is lunar underground caves and their skylight vertical holes as resources for humankind's expansion into space, presented by Junichi Haruyama-sensei. Haruyama-sensei, floor is yours.
Okay. So I will present this title, and I'm Junichi Haruyama from JAXA ISAS. Contents, and first introduction. This is Selene. Now, Selene discovered vertical holes. And there are 3 big, huge holes we discovered. One is Marius Hills, and another one is Mare Tranquitas, and backside, far side, Mare Ingeni. And perhaps the holes are possibly opened as a skylight of the cave, such as a lava tube under the ground. And like this. And I first say, lunar caves are treasure caves for science. Actually, yesterday, Mr. Nozawa, my student, presented the scientific interests of subsurface caves. First, you can see the strata layers exposed on the wall, telling us style and history of lunar volcanic activities and information of lunar paleomagnetic field. If you want to know the detail, please ask Nozawa-kun and me later. Anyway, and another point is inside of the lava tube. Inside lava tube is formed by the fresh rocks forming, and probably these lavas probably have been holding lunar endogenic from the inside volatiles, such as water and deep mantle materials without brecciation. And actually, you know, already lunar samples from the Apple, we understood water discovery in Apple samples already, you know. And also the Chang'e 5 also found water from the samples of middle latitude. So that everywhere water exists. So that we can see recently mantle of the moon is wet. So that we may expect some water inside the rocks of the caves. Now, just a little bit of Mars side. Sorry, this is the Mars map, and already there are a lot of the holes and the lava tubes on the Mars, and especially I want to say Elysium one. On the foot of the Elysium moon, there are a lot of the holes like this. And the Elysium moon is in all time covered by the water, or surrounded by the water. So here there is a holes and lava tubes, so that we can expect something, you know, under the ground in all time, or maybe currently. Okay. Anyway, come back, lunar holes. And lunar hole is a good shelter, as I say. As I want to say, the environment of the surface of the moon is a harsh, actually fast meteorites. Actually, direct meteorite impacts are not so dangerous now, but because the possibility of the impact is very, very low. But we should be conscious about secondary ejector. And if there is impact, there are a lot of the high velocity small dust and rocks and hit the other places. So very dangerous. So such an inflatable structure on the moon is unrealistic. Very high risk of punctures, okay? And radiation. You know radiation is very dangerous, about 200 times larger than that of normal radiation exposure. Yesterday, Naito sensei introduced that one. And the Chang'e 4, from the Chang'e 4, there is similar result for the radiation experiment, radiation measurement. So that this value is not so, it is correct, we think. Anyway. So some people say, let's cover the base by the regolith. It's stupid, because dangerous, because there is a high energy cosmic ray particle hits the regolith and interact with the regolith, which producing the numerous high order radiation effect on people in the base. So be careful, don't cover so much. Okay, if the 4 meter or 5 meter regolith covering, okay, but 1 meter, 2 meter is not so good, or reversely bad or worse. So be careful. Okay, don't cover regolith so easily. Okay, and so the inside rubber tube is very, very safe, you understand. The roof protects people and the instrument from the cosmic rays, ultraviolet, meteorite bombardment, and hypervelocity ejector of impact. So, and the inside rubber tube is a very, very stable temperature. So I comment in last week session. Anyway, if you want to know that one, please ask me later. Anyway, so very great place here. And lunar cave is useful as lunar base construction, as you know. So Next one, the resource around the lunar vertical holes and lava tube. The lava tube places are lava places, so the Mare region. Mare region is rich in iron, magnesium. And also today, I want to say titanium. Here is a near side and large holes here, like this. And and this area is the characteristic is very titanium rich here. So titanium, these locations titanium rich, so which will be resources. Okay. And yesterday, the Tanaka sensei, Dosha University, introduced a very, very important result. If you miss, please ask him. He made an experiment, and he showed oxidized titanium is electrically reduced to the metal titanium and oxygen. And the power needed is only 400 watt for the oxidized aluminum. So the oxidized titanium reduction is more not so less electricity. You know the Serene solar panel produces 3 kilowatt, 3,000 watt. So 400 watt is, not so large. Okay. Only 4 watt is needed to produce oxygen that is needed for 1 person per day. So if we can have such a technology, we can produce oxygen, okay? And if you bring the light hydrogen, then we can get H2O water. So we do not need explore, mine, transport, store the water of the harshest polar region. We don't need to go to the polar region. We can get the regolith from everywhere. So we can get oxygen and water. Now, helium-3. Helium-3 is a source material for nuclear fusion. And helium-3 is predicted to be rich in the middle low latitude because where the solar wind flux per unit area is high, and also rich in the titanium-rich region where helium-3 is easy to be captured. So remember this area, perhaps helium-3 is rich. And some people don't know the technology. Now, many countries rushing to develop nuclear fusion technology. It's not a dream now. So if you if you have an interest, please ask such a scientist. And some countries provide information for the new technologies situation or current level. Okay. So in near future, we can use new energy on the moon, maybe. So last one, exploration to the vertical holes and the underground caves. Lunar holes and caves are useful, as I mentioned. There is a country which is officially saying we will go there. That is China. China has already, the China National Space Administration, published a concept, lunar base structuring, in June 2021, so 2 years ago. And in their stories, first step is producing a telecommunication facility. Perhaps I think it's a L2, Lagrange 2, because Lagrange 2 is covered the far side. The far side is cannot see from the Earth. Very important place, in a sense. And the next one is the lava tube. China is actually aiming lunar lava tube here. And the lava tube is cannot see from the space, also hidden. It's important, I think. So China's step-by-step is now first is perhaps the far side, and the next one is under the ground. So I found these movies. Actually, some scientists, Chinese scientists, provided this movie and a screenshot. And inside the lava tube, they make something. And astonishing or surprising thing is the next one. They say China fires penetrators at the moon, producing artificial holes to create entrances to underground. Very great. So like this. Yeah, I think it's not right. because it's a good technology demonstration. Because a rubber tube is 100 meter wide. So if such a technology is developed, very great for something, okay, by China. Okay, so it's I think it's not a dream. It's not just fake, but I think I don't know. So Japan is I and some colleagues, 50 people, scientists, engineers, aiming to explore the rubber tube calling Uzume. Sorry, today is not so our time. So please ask us later what is Uzume. Anyway, Uzume's full name is Unprecedented Japan and the World of the Moon Exploration. And Japan is Japan. In the future, after the moon, we will go to the Mars. So we change the moon to the Mars, and what the moon is Mars, so Uzume is okay. Okay. So our basic concept yesterday, Maeda Sensei presented. A result of our trade-offs, our final conclusion is go to the hole directly. So hole-in-one mission, yes, we can do, yes, we hope. Because our Japanese engineers' technology skills are very, very high. And next month, we will go to the moon by the SLIM. SLIM's accuracy is 100 meters, and the diameter 100. So a little bit improving, then we can get such a technology, enter the inside the hole directly. And the construction lunar base under the ground is becoming realistic, I think. So remember, this reaction, then not only oxidation, but also metal ion, metal titanium, metal something, metal aluminum, or metal magnesium. So yesterday, the Kajima Corporation provided this image. So this is a future work. No, I think this is not a dream. Near future, we can get such a one by the iron metal, titanium metal will be produced by at the moon surface. Okay, and this is a Taisei Kensetsu Corporation also provide this image. I think this is not a dream, not far. And we can create paradise here under the ground, I hope. Okay, now contents is a summary like this. And anyway, there are some summary. But finally, what I want to say is construction moon village, not the moon village, but also the moon city. Even the moon city under the ground is realistic. That's all. Thank you very much.
Thank you very much, Harem Sensei. I'd like to invite you one short question, if you have. Okay. No, thank you very much, Harem Sensei. Thank you. Okay, next presentation is, who is the presenter? Yes. May I have a name? Because I have 3 names as an author. Yeah. So you set up a PC. Okay, so next one is the unveiling lunar riches, quantitative framework for profitable moon missions and beyond, presented by François Dobrou. Just a moment for the setup PC. Yesterday night, the party was very cold, and you got the heat pack. And I got a lot of questions, what is that? And this was just pure iron powder. So if you open up and it gets an oxygen, and it's heated. So it's a simple one. But I like that, this kind of a simple technique. And recently, you can buy the reusable heating pad by the rechargeable one. And I'm charging this battery by a solar panel, and it's fully sustainable. Are you ready? No. Okay, so some technical issues, so I'd like to change the order of the presentation. And the next one is, you have a slide on the PC. Okay, so the next one is the sustainable development of a lunar moon market, presented by Bernard Hoing. Mr. Hoing, floor is yours.
We are all clear, and we checked during the break. That's a presentation. We always do that now. And so it's a pleasure for me to present a paper about sustainable development of the lunar moon market. It has been prepared by one of my students. She's a machine learning expert and also marketing expert. And she's working for me as a special project manager for using machine learning into space data and also space application. She's not here, but I will present for her. I have also added with her some element of how we can build together some of this element of the lunar moon market. Yeah. Hopefully, we will come back with Fatima Fazel next year because I enjoy so much this workshop, so much collaboration, so much project we want to do. I will come with the whole team next year. But here, Fatima was very sensitive to the fact of sustainable development when we are going to explore and use the moon. And so the principle is to implement eco-friendly technologies and practices and make emphasis on renewable energy sources, efficient water management system, and also responsible resource utilization. And that's something that we should be guided from, and we should practice on the moon even more than on Earth. And we can use some of these technologies and also this philosophy on the moon and show that we are exemplary when we are going to explore together, use and build the moon village. Also, in the principle, we want to take into account ethical consideration. We want to protect the cultural heritage, in particular, the historical sites that we have on the moon. And so this includes the Apollo and Luna landing site, also the upcoming landing site. We had some jungle landing site. I created also myself a landing site with our mission Smart One. We have our spacecraft in the Lake of Excellence on the moon. And okay, it arrived at a fast speed, but there are some elements from this spacecraft there, and this could be a kind of a monument of our cultural, scientific, and lunar quest. We want also to avoid harmful interferences with features that are on the moon. We want to protect as well the future scientific heritage. That's something that we are going to cover this afternoon in the science panel, where we want to protect the moon for future scientific generations in particular. And another principle that must guide sustainable development for the lunar market is something which is based on the collaboration among international partners, be them space agencies, private enterprises, scientific institutions, so individual, various stakeholders. And we have to share this goal, and that's one of the Moon Village Association, to do that for sustainable progress with benefits that can be shared to all humanity. Even more than humanity, what we do, explain the moon, can benefit the Earth as a whole, even the biosphere. You know, now we are with the climate change, we are endangering not only humans, but also various species that are on Earth. And we have to be responsible for this whole biosphere. And we are going to bring a biosphere to the moon, so we learn also practice how humans live with other biosphere elements. So this we'll do by sharing knowledge and expertise and coordinating effort for sustainable development of what we do in preparation for our mission to the moon, but also on the surface of the moon. Another aspect is education and public awareness to promote in our youth, in our public, environmental stewardship. We are on spaceship Earth. We have to teach all the population to take care of our spaceship, and also we have to be guided by scientific literacy. So every public, every member should be a scientist, and we are going to use the lunar opportunity to engage the public in some of this scientific literacy, sustainable practice, and to create a culture of responsibility and for lunar preservation. So, as for the success of the lunar moon market, we need to minimize the environmental impact, protect the cultural heritage, promote ethical practice. So, if you want to connect to Fatima, so there is a QR code and so on. You know, she's my IT special project manager, so she has access to all these tools. But also now, in practice, what can we do? We have created a platform in Europe, a consortium between universities and companies, funded partly by ESA at the beginning, where we had an office which was placed at the Business Innovation Center. So something a bit similar to Antax, very good. We have to work together. And also where we touch with the academic world, also with the industry. We work with a consortium called Euro to Moon, for instance. And we have collaboration with worldwide universities and partners. And we got money from the European Commission. That's great. So with this money, we developed a number of free resources for so universities, but also for the public at large. We have some master classes. We do some mentoring of young entrepreneurs and researchers and space astronauts. And we organize also some webinars and platforms. So yesterday I presented the fact that we have this curriculum that all of you can be part of this Eurospace Hub Academy, or maybe we are going to call it Earth Space Hub, because we want to expand it over the world. And if there are some areas where you want to get some additional knowledge, if you are a scientist, you want to learn more about technology, about management, about astronaut training, you can take some of these modules. And we'll discuss also with some Japanese partners at university how we could exchange this general training of a space expert. And I've shown, okay, one thing that you can do, just join some of our crew expedition where you can be locked in a moon base for 1 week with the international crew. This is a team, we do that all year long in Poland. You can also learn about not only science, technology, but medical, living on the moon. We have now built an habitat which is a moon base for 4 people that keeps traveling around in Europe. And we use an inflatable technology. I love the inflatable talk this morning. So we can expand by a factor of 3 the volume for the astronaut. It's now in our Business Innovation Center, but we want to duplicate this. And eventually we do one in Japan, and we'll bring it to some of your center. It's great for training researchers and also for outreach. We have also our moon base in Hawaii, International Moon Base Alliance. We have our director of operation, Kato Kless. She is looking for candidates, individual astronauts, researchers, entrepreneurs, or companies that want to go there to test some of your equipment. We want to make that available for the Japan Moon Village and International Lunar Market ecosystem. You can train your students for EVA, for doing research. We survived giant eruption, so we are still there. We had mission at the beginning of the year, led by Enclosures, which is quite famous in Japan as well, because he's a Tetris owner, and is investing into exploration and sustainable development. And so, as an example, we have last year funded a number of research interns on various topics of space research, but include even a topic of space diplomacy and regulation, looking at new space economy between US and Europe. We are going to do the same, Europe and Japan, and see how we can work together, application of machine learning for the market. And we have also special project manager we give funding to, like the one that designed our moon base, like Kato, that is our director of operation, and various. And we have some job available for young professionals that want to take part in our project. We could also fund some special project manager in Japan for collaboration. So these are some of our initiatives. We even have an art and space initiative where we developed a gallery of art that we want to send to the moon. And it's called Moon Gallery, 100 pieces of art in a miniaturized tray. We launched it to the International Space Station. We are looking forward to launch it to the moon, but also to include some Japanese art scientists on board. So now I want to finish with the first slideshow. Internationally, we are very involved in organizing the International Astronomical Congress. We had a great one in Baku. Next one in Milano. Please submit abstract into the lunar session, which are organized, or other sessions. We are now an office in the Business Innovation Center in Estec. So please come and visit. Let's develop some project jointly with Japan and with the Moon Village Association community. We are also part of a bigger campus, Space Campus Netherlands, working with some universities and industry which are there. And we have a number of key partners like Toulouse Aerospace School. So I have some 60 students there that are developing some various projects. And we also have some good collaboration with Bremen. So we had a great Space Tech conference there. And we have also Dublin as a key partners. They send me 6 students for the next cohort that are going to work on our moon base. So what about EuroMoon Mars, Moon Village, and Japan? Join our Eurospace Hub program, training program. Let's create Japan Moon Mars, and as a collaboration, joint international event and project. We have some. We want to build on past and ongoing collaboration between ESA, JAXA, NASA, and other projects. We want to give you access to our moon base in Hawaii for tests, for astronautics, for improving the technology of your experiment. We'd love to help setting up an equivalent moon base in Japan, or even bigger, because I think you have so much potential, so many actors. We'd like to help in a possible moon-based analog that could be in Japan and develop collaboration with Japanese stakeholders. And we are very impressed by the lunar market ecosystem in Japan. And we need to contribute. And so some of our collaborators are ready to move in here and contribute. I see also there is a good international community that have now are working in Japan. They told me a lot of good. And so we want to contribute to this lunar market. And also in the frame of Moon Village Association activities and project, we can also enhance what we do. For the young professional here, I see great contribution. I think also there are opportunities to be connected to Space Generation Advisory Council. Let's have a branch in Japan. I am a founder of SGSC some 25 years ago, and I see it's developing very well. In Japan, it's not so present, because maybe you're very busy doing the real work, but it's also important to network with the other young professionals over the world. So again, I want to end with just this slide. I'll leave it for you to consider. This is the planning of activities that we have next year. We have some event at ESTEC. We have some event at the European Geoscience Union. We will have COSPAR in Busan in July. Please submit abstract from your presentation. And we'll have also an event in Milano, ISE, in October. And what about coming back next year in November, having an event of this class, but even including some training, some partnership, looking at some hardware. I'm looking forward for the next step of working together on sustainable development for lunar market, and also in collaboration with our Japanese and Moon Village Association colleagues. Thank you very much for your attention.
Thank you very much, Bernard. Any question?
So who wants to join Japan Moon Mars?
Yes. Question? No. Okay. I think we have time, but okay. So thank you very much, Bernard. So the presentation, third presentation is ready on a PC. So I'd like to invite third one, unveiling Lunar Riches quantitative framework for profitable moon missions and beyond. To be presented by Francois Dublin. I hope I pronounce your name correctly. Okay, ready? Okay, Mr. Dublin. Floor is yours.
Okay, bonjour. Yeah, in France, we say that if you want to keep your friends, never talk about money. Okay. Unfortunately, you know, I'm the guy who's going to talk about money. So I hope I will stay friend after that. But I will explain you why, because our program, I will briefly mention to you, of course, there's a lot of technology behind that. There's also this endeavor to bring science on the moon, to develop infrastructure. But today we try to address this money issue because for a company to survive, you know, economically, you need to produce profit because this is the only way to attract investors. I don't know how it works. Let's do this. Yes. Okay. Fantastic. So there's a photo on the top left about our vehicle. So our company is called Cosmosis. The headquarters is in Singapore, but we have 2 subsidiaries, one in France, in Toulouse, and another one in the US, in Texas. So Cosmosis' purpose is to focus on the design and the development of a vehicle we call the Zeus X. So you know that Zeus is the father of Apollo and Artemis. And we've been developing this vehicle with Airbus Defence and Space. And the purpose of this vehicle is because it's an assembly of 2 sub-vehicles, I would say. So you have a service module, you see with the solar panels. And with this service module, we can inject microsat and also operate instrument. And on top of this service module, we have a lander. And this lander can land on the moon something around 800 kilograms of payload, which sets our vehicle on the top class of this kind of mission. And of course, when you develop this kind of vehicle, you always think about what's the extension. So of course, you know, the commercial purpose is to bring payload of our customer on the moon. But we also think about deploying our own payload. Of course, it's very complicated. Everybody in the room, with all the presentation we've been having since yesterday, knows that it's very, very complicated. And for that, of course, I will not talk about the complexity of the technical aspect of it, but also the complexity of the economy. Again, I mentioned that how can we develop a business case that shows that it's profitable enough? So how to at least attract the eyeballs of investors and trying not to say things which are not part of a vision or a sort of a guessing game, because nobody can predict the future. So we need to have a certain level of information and data before going forward and before making some choices. Essentially, when we try to put some numbers, or we try to put some equations, even though not scientific but financial, it's a non-linear problem, and mostly for 3 reasons. First reason, actually, it's very connected to the story of our company. When, after we launched the development of our vehicle, we discussed with scientists and also engineers, also entrepreneurs around the world, and said, okay, what do you think of, for instance, extracting helium-3, on the moon? And we have the two extremes, On one end, people say, oh, that's fantastic, that's great, this is the future. On the other hand, some people say, oh, that's a stupid idea. And whatever their opinion, I ask, do you have data on which you can rely? And no one had data, okay, or strong data. People came with their own opinion. An opinion is not enough when you develop a project. And it's not blaming anybody, but the data are very scarce. So for that, we have to, and it's very connected to the second point, is that we really have to embed into our thoughts for deploying a viable business case the risk attached to it. Okay, so the risk of the unfortunate event that can happen to your system, but also simply the risk of what you extract, what it is made for, who is going to buy it. And the third factor, and everybody knows about this factor in this room, is that when you launch a space solution, the maintenance is very limited. And there's many single point failures, as everybody knows. So that creates a lot of non-linearity things. So, of course, the easy solution for everybody is say, okay, I put numbers, in a cell, on a spreadsheet, and the investors or the engineers or whoever would be happy with that. But it doesn't work like that. And, the Excel spreadsheet, Microsoft doesn't help, in other words. So the logic, the very basic logic to make a business profitable, or at least which work, is to have a piece of asset, and when you improve this asset over time will create slowly your profit of tomorrow. And the example that everybody knows, are infrastructures. Okay, you have a plane or you have a building. There's also a geostationary satellite, which is another thing I will mention briefly about. But you buy a house and you lend your house, okay? And time will create, bit by bit, your profit, because with a rental you will reimburse, of course, your investment into the building, and after a while you make profit. So this is basically how infrastructure works. So for everybody's familiar, and I'm sure everybody's familiar in this room, you have this curve, this straight line that is dependent on time, okay? And that space is not very familiar, with this time or assets, improve over time. Again, the exception is probably geostationary satellite. So you know that the geostationary telecommunication satellite is now quite a very settled business. And of course, the longest they have their satellite in orbit, the higher their profit. In short, forget about this graphic, but for the numbers of the equation that will follow, we can briefly split a program in two. So you have, of course, the setup from T0 to T1. So the setup is like preparing my view graph, you know, to present to you today. So you need a bit of time. This period number one, of course, you know, this is the manufacturing of your spacecraft, the design, manufacturing, the launch, and arrive on the moon. This is a deployment. And after that, the period two is simply the period of operations. What makes the difference and what creates the non-linearity are this system reliability. Because everybody knows that it's a decreasing exponential, according to a decreasing exponential law. And this lambda, this constant lambda, is supposed to ensure, on a statistical point of view, you know, the fact that your system is going to work or not. So everybody's familiar with the financial project, and even in big corporation, in big tech corporation, there's this net present value standard model. Okay, I will not go too much into detail, but this model doesn't implement necessarily this risk, you know, we can I described earlier, especially for space. So what we did internally before, instead of Cosmosis, you know, instead of getting into an Excel spreadsheet and trying to put a lot of numbers into cells, you know, we try to think about how can we make a sort of a correspondence, because what's standard, what is admitted by everyone, and how can we translate it into something that makes sense for a space project. So we will not, of course, focus too much on this equation. The first part is focus on the revenue. How can we make sure that the revenue are not necessarily subject with risk? One thing to the takeaway of this view graph is to focus on financial derivatives. So it's a financial instrument that can make sure that you can try to create at least a sort of a cash flow revenue very, very early on for very remote product you can deliver. So in other words, if you extract helium-3 and we intend to start or to prototype, you know, helium-3 extraction by 2028, we believe that, yeah, we can produce something substantial 10 years after. So it's a very, very long time. So for that, you have to define today, to limit your risk, you have to define an approach, a financial approach to produce that. You have this A0, which corresponds to the productivity of your system, your rovers that can crawl the moon. And I can mention that this Tsukimi project is very interesting for us because it will determine our A0, you see in the equation. So just to mention that it seems to be a very boring equation, but behind that, there's a lot of science, there's a lot of technologies that can determine the parameters to this. Obviously, something, you know, will not go into detail. You see the non-linearity in the equation, the risk part of this equation, the cost equation. This is a risk that creates the non-linearity actually in all systems. And every project on Earth, you know, has its own cost part, you know, related to risk. But on the Earth, the risk attached to a project is rather limited, and on top of that, you can maintain a system that fails. In space, it's not possible. So that's why it becomes a parameter which is very apparent, and therefore that creates complicated equation. So we come down to this binomial expression that is very helpful after that to calculate our cost. So the conclusion of all this calculation that helps Cosmosis, you know, to assess more or less, you know, the way we can make a viable project come to this equation. Again, it seems to be complicated like that. It's not really complicated. And we apply this approach on our own system. our system which intend to extract noble gases, so including helium-3, and it gives roughly a time frame for making a viable project on the moon. You remember my story about a building or my story about an aircraft. We come down to the fact that with a acceptable level of profitability, with an acceptable level of risk, we believe that the mission itself would last a decade, okay? And so that's why it brings after that many factors that can assess the technology that makes your system. So that means that when we design a system, you must design a system that the thermal, the radiation, and other parameters must stand a period of 10 years, okay, for us, for our project. But this set of equations are pretty useful to make sure that you can go in front of investors and show that you have something which is pretty solid in terms of solution. So this kind of equation after that, can be more complicated. We can improve this work on this system of economic equation. We also improve, the Lambert function, so we come to the top of what could be complicated in terms of mathematics. But the option pricing for the derivatives is also an important factor. Real option is also something that researchers, like to think, to talk about. Lows and diminishing return is also another factors. The takeaway of this presentation, sorry, maybe I'm a little bit long, I don't know. You will stop me. So risk is such a dominant factor in space, and everybody in this room knows that this must be the primary factor for designing a system. And of course, financial derivatives on the revenue side is another important factor. And on the cost side, we need to work first on the mathematics. And after that, we can go to the Excel spreadsheet and put some numbers, if people like it. Okay, and that's it for today. Thank you.
Thank you very much. Any question? Yes, please.
You said that we should not use Excel. Which tools do you use for making the calculations? Or it's just the equations and then you implement them in the Excel?
No, it's a very good question because it seems to be confusing, because putting equation on a piece of paper, you say, oh, Excel can solve that. My point is much more on the fact that we must think before putting numbers in an Excel spreadsheet. How do we assess, our level of risk, And sometimes the numbers are not very helpful, I would say numbers with decimals into an Excel cell, that doesn't help, Or in other words, you can say, oh, maybe, I would make 10 million next year or 20 million, How can you justify that? So before getting to that, you need to be systematic. You need to have a methodology. Okay, and that methodology we try to develop for ourselves. Okay, make sure that we don't do big mistake, and we can at least, we never guess about the future, but we can rather justify, what we do. Does it answer your question?
Yes, okay. Thank you.
Thank you, Matt. Any more questions? Okay, thank you very much. Thank you. Okay, next presentation is development of an unmanned exploration robot for topographic survey and geotechnical investigation on the lunar surface, presented by Taizo Kobayashi-sensei. Kobayashi-sensei, floor is yours. Okay, so last one technical problem before the lunchtime. Please be patient. And next presentation actually from video. And so lunar construction development to be presented by Mr. Raymond Clinton of NASA. Okay, so ready to play. Okay, ready to go.
Okay, please go ahead.
Great.
Okay, please go ahead.
Great. Although I can't be there with you in person, I did have some information that I would like to share about NASA's Moon to Mars exploration strategy and objectives, and also the Space Technology Mission Directorate's recent initiative that they've announced. NASA has developed a Moon to Mars strategy. They did this by not only internal planning, but also holding several workshops in which they requested input from other space agencies, other government agencies, large businesses, small businesses, and even private citizens, as well as academia, lots of universities and so forth. And they got over 5,000 inputs. They sorted these inputs into 63 objectives. And those objectives address things such as transportation and habitation, science, operations, infrastructure, and recurring tenants. Additional information on first of all, let's go to the link that's in the chart. That's the link that you can follow to see the report on the Moon to Mars strategy and objectives. And then down below that, there's the architecture definition document, which is basically a deep technical dive into the architectures that are envisioned for the Moon to Mars strategy. In addition, there's a series of 6 white papers that provide additional information on the strategy and the objectives. So let's go to the next chart, please. Okay, I've put together a few of these objectives that deal with construction and also manufacturing. But it's important to note that the way the strategy was developed was to architect from the right, develop and execute from the left, and stick to the plan. Now, I do want to point out a couple of these objectives that are LI, meaning lunar infrastructure. The first two there, demonstrate advanced manufacturing and construction capabilities in support of continuous human lunar presence and a robust lunar economy. Now, that is a rich statement that is really very powerful because you're talking about demonstrating these technologies. You're calling out specifically manufacturing and construction, and you're talking about a continuous human lunar presence and a robust lunar economy. There's just an awful lot to focus on in that one. In the next objective, the one right below that, demonstrate technologies supporting cislunar orbital surface depots, construction and manufacturing, maximizing the use of in situ resources needed for continuous human lunar presence. Again, the continuous human lunar presence, and again, the emphasis on construction and manufacturing technologies. The other point that's very important about this is maximizing the use of in situ resources. The other objectives that I've shown here deal with understanding the impact of the lunar environment on the system and on the materials. But when we get down to the last two, and OP stands for operations, you'll see again, there's this recurring emphasis on minimizing the amount of materials that have to be launched from Earth and maximizing the use of in situ resources. And then for the last one, it talks about for those materials that we do launch from Earth, we need to make sure that they are recyclable and reusable when they get to the moon. Let's go to the next chart, please. This chart was shown recently this fall at the Lunar Surface Innovation Consortium fall meeting. And this was an announcement that was made by Space Technology Mission Directorate. You'll see in the upper center of that chart, there is a lift one that is with a red circle. LIFT stands for Lunar Infrastructure Foundational Technologies. And this is the first mission that will demonstrate those technologies that is supported by Space Technology Mission Directorate. The primary objective, the primary focus of this mission is to demonstrate the capability to produce oxygen from the in situ resources there on the moon. Additional objectives include excavation, feeding the oxygen production machine, power, autonomy and robotics, dust mitigation, and construction is also an optional objective. Now, by option, what is meant by that term is the others are primary, and if construction technology demonstration can be accommodated in the mission architecture, then there will be essentially bonus points added for including that technology in the first mission. Now, for this mission, STMD has put out an RFI, what we call an RFI, which is a request for information. They're asking industry to try to understand the interest of industry in participating in an RFP, which would be a proposal call as a result of the information that they get when they put together, or when they analyze all of the information that they get back from the RFI. And that RFI is due on December the 18th. So it's active right now, and it was just released within the past couple of weeks by STMD. So looking forward, the plan is that STMD will structure a request for proposal, RFP. Industry and industry teams will respond to that RFP, and a selection will be made for the technologies that will be demonstrated on this first Lift 1 mission to the moon. Do we have the next chart, please? So for the IMPACT project, and I happen to be the principal investigator for IMPACT, and that stands for Moon to Mars Planetary Autonomous Construction Technologies. This is our vision. This is how we view architecting from the right. You can see in the foreground is a machine that's building a landing pad. We believe that the landing pad will probably be among the first structures created on the moon. Planar structures followed then by roads. And you can see over in the upper center, there's another machine there working on a roadway. And then farther behind, you see another machine working on a vertical structure or a habitat structure. And chronologically, that's how we see the development of this capability on the surface of the moon, starting with the planar structures being the landing pads and the roads, and then moving to the vertical structures like shelters and habitats. Let's go to the next chart, please. So coming back and executing from the left, this is how we began to develop those capabilities. First, we evaluated a number of different materials and processes, and you can see the types of those materials listed there. Cementitious materials, which require a binder. We would use the lunar regolith as an aggregate in the cementitious materials, but it also requires binder materials like calcium sulfoaluminate or magnesium oxysulfate, just as an example of a couple of those binder materials. To be able to produce large complex structures on the surface of the moon, number one, you would have to have an industrial scale beneficiation capability to produce the binder materials, because you certainly wouldn't want to launch those from the Earth. It would be tremendously expensive. But it will also have to be operated in a controlled environment to keep it away from the vacuum and extreme temperatures of the moon. The same is true with the geopolymers and polymeric materials. We also evaluated thermosetting materials like, for example, an aluminum graphite mixture. And then we started taking a look at the technologies that would not require any materials to be launched from Earth. And those are the directed energy deposition methods. One of those is regolith melting, where you just put regolith in a furnace, you melt it and extrude it, much like you would a 3D printer. Another is laser centered, where you use the power of the laser to center and melt the regolith that is on the surface of the moon. And then finally, there's microwave centered, again, using the microwave energies to center the regolith on the surface of the moon. We evaluated these materials and looked at the mechanical properties and also the thermal performance. And when we did, we selected laser centering as the baseline, and we're continuing development on the regolith melting and also the microwave centered as risk mitigation processes. Can we have the next chart, please? One of the evaluations that we performed, and hopefully you'll be able to see this, that's our plasma torch test facility. And what you can see there is the plasma torch applying a certain level of heat flux onto the sample. That was a laser melted sample that was created by Icon Technologies in Austin, Texas. They are our primary partner. And what you can see on the left-hand side are surfaces of those samples after they have been tested, before and after. And you can see the pre-test and post-test as it's identified. Now, the machined and as fabricated simply means that we machine the surface of the sample flat, and as fabricated was the more rippled surface that the process created naturally. The good news for this material in terms of its thermal performance is that there was negligible erosion after the exposure to this heat flux, and the weight loss was measured in hundredths of a percent. We got the heat flux that we applied to these samples by taking the information from the exhaust gas from a large cargo lander nozzle on the engine on the spacecraft, converted that to a heat flux, and then we applied a safety factor to the heat flux and tested that for the duration of the landing profile. Again, outstanding performance by this material. Next chart, please. So the next step for the project would be to test the hardware in a large vacuum chamber that we called V20, thermal vacuum chamber, here at the Marshall Space Flight Center. It's 20 feet in diameter and 28 feet in length. We will be doing two tests in this coming year. The first will be in February, and we're testing the robot arm. The purpose of that test, the objectives are to understand the thermal management and the kinematics of the robot arm. Then in the fall, we'll test an engineering development unit for the system that we intend to send to the moon, and we'll run it through its paces. It will have a tray of regolith material in there. We will operate it at the temperature conditions we expect to see on the surface of the moon and a high vacuum level that's representative of the vacuum conditions that we'll see on the moon. It's very important for us to test this hardware in the operational environment that it will see on the moon, so we have much greater confidence in understanding and knowing that this system will perform well once we get it to the moon. Because there are some questions that we have to be able to understand. We're simulating the environment, we're simulating the materials, and we want to be able to prove in this first proof of concept demonstration on the lunar surface that these simulations that we've made for our Earth-based test are actually good analogs for the operational environment that we'll see on the surface of the moon. So in the fall, in the August test, we will have the end effector, we'll have the laser, we'll have the appropriate instrumentation that we need. We'll have the scoop, tamp, filter tool that will actually scoop up the regolith, filter it, create the feedstock, and then we will center the feedstock. We'll make test articles to make sure that we understand, again, the mechanical and thermal performance from the samples that are made in that environment. And we'll run the system through the full paces that it will be expected to see when it gets to the moon. Next chart, please. And I believe that's the end. If I were there, I'd be happy to take any questions. But I hope you all have found value in this presentation and that you'll be able to go and take a look at NASA's Moon to Mars exploration.
Thank you. Okay, so this is the last presentation this morning before lunch by Taizo Kobayashi Sensei of Ritsumeikan University, who will present the development of an unmanned exploration robot for topographic survey and geotechnical investigation on the lunar surface. Okay, Kobayashi Sensei ready? Okay,
Yes.
Please.
Hello, everyone. I know the session time is already over. I think you are all hungry, but please be patient. I will make my presentation as quick as I can. So, I am Taizo Kobayashi of Ritsumeikan University. I specialize in civil engineering with focus on geotechnical engineering. Today, I am going to talk about a robot for geotechnical investigation on the lunar surface. Before I get into the detail of our project, I would like to provide a brief overview of geotechnical engineering and the importance of the geotechnical site investigation. On Earth, constructions of civil engineering structures or buildings involves various soil-related operations. For example, earthworks such as soil cutting, excavation, earth fillings for road constructions, ground improvements, and foundation works, etc. These are all geotechnical engineering. And I teach a class on soil mechanics at my university, and I teach a theory how to predict the pressure acting on the retaining wall by using this equation. And I teach the theory to predict the bearing capacity to support the load of the building. And I teach the safety factor to analyze the slope stability. So in these equations, you will find some parameters such as gamma, phi, c. These are the parameters of soils that define the mechanical property of the soil. So in order to use these equations to predict the soil structure interaction, we have to know the value of these parameters. To obtain them, we usually conduct a soil investigation on Earth. On the moon, we know that the lunar surface is covered with very, very fine, dry, granular material called regolith. And the average of the particle size is around 70 microns. And these particles have rugged shape because there's no aberration due to the wind or water on the moon. So the characteristics of the soil will differ compared to the terrestrial soil materials. So unlike the previous remote sensing exploration,
the future lunar surface exploration will also involve soil-related operations. But the lunar surface still has many mysteries. There are many, many uncertainties. So understanding the soil properties of lunar regolith and predicting the behavior of regolith machine or regolith structure interactions is crucial for the future lunar activities. So we are currently developing a robot for topographic survey and geotechnical investigation to create a three-dimensional geological and geotechnical map. And the data will be used to predict the behavior of robot regolith interaction or robot structure interactions. This is the robot that we are developing in our project. We have 4 investigation tools mounted on the rover. We have developed the rover having a robot arm, but we think these are just a platform for mounting the instruments. So we are not focusing on the development of the rover, just a cart. So again, the system has 4 investigation equipment tools: positioning and surveying tools, active seismic exploration tools, density meter, and loading and shear testing tools. By combining these instruments, these investigation, I think we can achieve the effective assessment with the least amount of resources. So I'm going to go into the detail of each tools. The first, we are developing a positioning and surveying tool to create topography, 3-dimensional topography on the lunar surface. On the moon, we have to establish a method for surveying without using GNSS. So in our project, we propose the combination use of camera and radar to create a precise topographic 3D map. And second, active seismic exploration tool. We think it's very important to know the spatial distribution of the bulk density of the lunar surface because it greatly affects the mechanical behavior. So we are developing an active seismic exploration tools having such a ultra small arrays based on the surface wave exploration techniques. By analyzing data, we can obtain the S-wave velocity structure for the vertical direction at the measurement point. And it takes about a few tens of seconds or something like that, very short time. I will skip that movie. And next, RI density meter. We are developing a small device for measuring density, bulk density, by using a gamma ray. So that's the device that we developed. It's very compact, fitting in the palm of my hand. To measure the bulk density of the surface of the ground, it's very simple. You can simply put the box onto the ground, just it. It takes a few minutes to measure the bulk density. And lastly, loading and shear testing tools to measure the mechanical property of lunar regolith. It has 2 functions. One is the loading test to obtain the information about stiffness and compressibility of lunar regolith, such as modulus of subgrade reaction and Young's modulus. Another function is rotational shear testing to obtain the information about strength of the regolith, including cohesion and internal friction angle. So this system has just been completed very recently. So unfortunately, I don't have results to share with you today. But back in March 2022, we performed a trial experiment using the first model, the initial model of our investigation tools, as shown in these pictures, by using a handy cart. And we create a model artificially. We made a depression in the center and filled with another soil, and we made a compaction by using the machine to create the ground having a different stiffness or density. And this is the result that we could obtain from the experiment: three-dimensional S-wave velocity structures obtained by the seismic exploration. We know that S-wave velocity is correlated with the stiffness or soil density. So we think this is the representation of the distribution of the stiffness in the ground. Next, the left figure shows the two-dimensional distribution of the measurement value obtained of our instrument. And the center figure shows, the top figure shows the predicted settlement of the something put on the ground by theoretically calculated from the measurement coefficient of subgrade reaction that was obtained from our instrument. And left figure shows the distribution of bearing capacity from the internal friction angle, cohesion, and bulk density. And what I wanted to say is that we can contribute, we can, by doing the geotechnical site investigation, we can contribute to identify, for example, the safe landing area or landing the place for the lunar base construction. Okay. In conclusion, again, on Earth, geotechnical site investigation is a standard procedure at the very beginning of the construction works. So we think the similar process is needed on the moon to ensure safe and efficient lunar activity. So the week after next, we plan to perform the validation experiment in the field. So I think I look forward to sharing the results with you next time. Thank you very much. That's all.
Thank you very much, Kobayashi-sensei. So we are already in the lunch time. So if you have a question for this presentation, please ask him personally. So thank you very much, and let us a little bit squeeze lunch time, and we will start at 1 p.m. Thank you very much.
Okay, let's go to the lunch. So I can give you guys the lunch avenue. So lunch avenue is the same with yesterday. So if you know, so please go to the lunch avenue. So for those who did not join to the yesterday's lunch, so I can make guidance. So the lunch venue is different from this building. So in the Geibunkan, we have a lunch venue in the Geibunkan. So we have some staffs for guidance for you. So please go to the around the Geibunkan. Then you can find our staffs. If you have some questions, so please contact me, please.
Please. すいません。落とし物された方いらっしゃったら見つかってますので受付までいらしてください。落とし物された方いらっしゃいましたら受付までお願いします。
There. Okay. Good afternoon. Welcome back for this final afternoon session of the Moon Village Association 2023 Workshop and Symposium. We have a special guest lecture this afternoon from Kanai-san Norishiki. Norishiki, is it correct? Yes. Is it pretty close? Kanai-san anyway. So, Nemo. So I was asking him, he said he goes by Nemo, and I asked him which Nemo, because in the West, there are two Nemos. One is a young boy who goes through his dreams, adventures in slumberland with little Nemo, but there's also Captain Nemo, the inventor of the submarine and one of the great sailors from Jules Verne, from 150 years ago. So I think we agreed you are more like Captain Nemo because your background is in the Navy. So please.
Thank you very much. Okay, thank you very much for the introduction. And I'd like to, first of all, I'd like to thank Inatani Sensei for inviting me for this special opportunity and giving me a chance to speak in front of you all. And this is a very honor for me, and I'm a little bit scared in front of these professors and senseis and people. And thank you very much. Anyway, and also usually in this symposium, speakers are given only 15 minutes, but he gave me 30 minutes, and I thank the generosity of about that. And Inatani Sensei gave me a title, Let Us Go to the Moon, which is a very exciting title and a fun topic to talk about, and I'm very pleased with that. In this presentation, I'd like to look back the past and overview the current JAXA's human space activity, and to think about the future exploration. And this is not an academic presentation or anything, so please be relaxed, sit back. And for especially the students from the universities and the institutes, there's no note-taking required and no testing, so we relax. And together, we will think about the future exploration. Okay, starting from the history, it was back in 1961 when Yuri Alexeyevich became the first human flight to the space. And within that decade, mankind achieved the first lunar landing in 1969. And some of my senior colleagues in the office often mentioned about childhood memory about the moon landing. But I was born in 1976, so it's before I was born. Then for me, these events are only historic events, and only in the history books or documentary films. But anyway, yeah. So for me, the astronauts at that time is historical figures. And the picture here, on the background picture here, that was I took from the space station when I was up there in 2018. Then I was so astonished how big our Mother Earth is from the space station, and this tiny dot is the moon, And I also understood how small the moon looks like, and understand the distance from where we are now. And the Japanese manned space program started in 1985 when first generation Japanese astronauts are selected. From left to right, Mamoru Mori and Chiaki Mukai and Takao Doi. They are selected as first generation Japanese astronauts. And when they were selected, I was in elementary school, and I still have a vivid memory about them holding a mini space shuttle in their hands and speaking about the upcoming future missions and prospective futures in their press conferences. Then one unique point of Japanese space program is that it was started with idea of peaceful space utilizations and completely separated from military activities. And that's why they are scientists and medical doctors and not military aviators at that time. The first generation Japanese astronauts flew to the space as payload specialists. Maybe young people does not know about the term, but the payload specialists are responsible for the scientific researches and experiments on board the space shuttle. And they are purely for the scientific experiments in space. And to me, these people, Mori-san, Mukai-san, Doi-san, they are more realistic hero rather than the historic figures and role models. And definitely they were inspired. They inspired children and young generations at that time. And Mamoru Mori on the left, flew 1992 as a very first Japanese professional astronaut, and he also flew second time in 2000. And Chiaki here. She flew space shuttle twice, to 1994 and 1998, and she became the first Asian female fly to space. And by the way, she flew with John Glenn here. When he flew, he was 77 years old, and I still remember Chiaki and John Glenn walked out from the crew quarters, and that was my the first memory thinking about, dreaming about the space program. Then, as time passes by, Japanese Space Agency continues to select and train astronauts, and 1992, Koichi Wakata was selected as a second generation. Then following him, 1996, Soichi Noguchi was selected. And astronauts from other countries called them Ichi brothers because Koichi and Soichi, and also they are oftentimes they together trained in space shuttle and Soyuz Russian training. And also their common theme of them are they are both engineers, not the scientists. That's a little bit change from the Japanese astronaut corps. Then in 1999, the fourth selection was made, and starting from left, Satoshi Furukawa and Naoko Yamazaki and Aki Hoshide, they were selected. And this time, also Naoko and Akihiko, they are engineers. Satoshi is a medical doctor. Then 2009, fifth selection of JAXA astronauts, Takuya Onishi from Japanese airline pilot. And Kimiya Yui is a colonel of Air Force test pilot. Then myself from Japan Navy as a diving medical officer. And yes, Japan has total 11 astronauts so far. And the background or specialty in the previous job has changed a little bit from the first generation. We have 4 engineers, Koichi, Soichi, Naoko, and Aki, and 2 pilots, Onishi and Yui. And there was a reason behind that, in my opinion. NASA started to provide opportunity for non-American astronauts to fly space as an operator who is called mission specialists. The mission specialists are responsible for spacecraft operations such as extravehicular activities or robotic arm operator or support shuttle commander and the pilot as a flight engineer. And that's that big change for astronauts all over the world. And the Japanese government quickly changed their course and trained their astronauts to be an operator in space. And Takao Doi, he's a first-generation astronaut. First, he was selected and certified as a payload specialist, but he recertified as a mission specialist and flew on the space shuttle. And he became the first Japanese spacewalker. Also, Koichi selected as a mission specialist, and he maneuvered the space shuttle robotic arm to capture the free-flying satellite as a first Japanese. And Naoko flew on space shuttle Discovery to be a second Japanese female astronaut. Then time passes again. Then astronaut's job also changed quite a bit. Now is a time for the International Space Station, and the majority of astronauts fly to the ISS for long duration missions. And that long duration mission typically lasts about 6 months. 6 months long. It's very long. And in 2009, Koichi made the first Japanese long duration mission in his third mission. And from that, we have many long duration missions. Up until today, Satoshi Furukawa is on board the space station for his second flight. And we've just celebrated his 100th day in space this week. And in 2 years, Kimiya and Onishi, my classmate, will be on the space station in second time. And I hope I will go back to space near future. Anyway, there are remarkable, couple of historical missions in these missions. Of course, all missions are, every missions are historical, especially my mission 2017. It's personally most important mission in this chart. But from the Japanese astronaut point of view, there are a couple of highlights. Koichi became the first Japanese, the ISS commander as Japanese in 2014. And pilot astronaut Kimiya and Takuya flew Russian Soyuz spacecraft as a left seater, which is the pilot seat. And also Soichi, another Ichiichi brothers, flew first US commercial flight to the ISS in 2020. I was working family support for him, and I visualized him walking out of the crew quarters with this nice SF-like spacesuits, and it was so cool. I was so excited at that time. I still remember. And Aki became the second Japanese ISS commander in 2021. So now, this year, early this year, JAXA announced the newest astronaut candidates. Ayu Yoneda on the left-hand side, the lady, and Makoto Suwa in the screen. They are the newly selected Japanese astronaut candidate for now. And the selection was the largest in the history of Japan space program, and more than 4,000 people applied for the astronaut position. And we got a big attention from all over Japan. And this is a nationwide campaign called Hello Explorers Project. And why we got so big attention, actually the NHK, the leading TV company in Japan, filmed the documentary of this selection process and broadcasted as the selection process went. So why we got such a big attention from all over Japan? Partially because the JAXA lowered the bar for applying to be an astronaut. In the past, the only natural science and engineering and medical fields are allowed for the application. But this time, first time in the Japan history, JAXA accepted the applications regardless of academic background. That's one reason. And still the requirements or standards to be an astronaut hasn't changed, and the selection process hasn't changed. It is still very competitive. Out of 4,000, only 2 were selected. But apparently, Japanese people liked the JAXA's decision to open up the opportunity for everybody. And I like this chart because over 60s, 69 people applied. Over 50s, more than 400 people applied. And it's very promising. And actually, I was 47 years this year, and Suwa-san, newly selected astronaut candidate, he was the same age like me as me, so classmate. So another reason, another backdrop was governmental policy toward the lunar exploration. All of you already know, in 2020, October, JAXA, or Japanese government, signed Artemis course. And about 2 years later, last year, Japanese government and the US government agreed for the cooperation on the lunar gateway, and also they agreed to send the Japanese astronaut to the moon. It was very exciting news for me and for everybody in Japan. And that's why the newly selected astronaut candidates are so popular in Japan, and they were unofficially called Artemis generations. And just like Mori-san, Mukai-san, Doi-san inspired me and our generations, and Yuri and Apollo astronauts inspired the world, the newly selected Japanese astronaut candidate is a hero for the young generations right now in Japan. Okay, then back to the current destination, which is the International Space Station and the Kibo Japanese Experimental Module. And it is on orbiting outpost for mankind. And more than 20 years, the astronauts from all over the globe flew to the space station and continuously stay there and conduct cutting-edge experiments and scientific researches. And we usually hear the phrase, okay, the International Space Station as a testbed for the future exploration. And I think it is also true, not only for the technology development, but for the astronauts' activity. It's a good test place and a training place for the future exploration. And the physical changes and space medicine, unique environment in space, such as microgravity, radiation, artificial habitation environment are a big challenge for human physiology or human body. And bone, for example, the bone and the muscle became weaker and weaker as astronauts stay in space. And the astronauts have to exercise 2 hours every day. And inside the Kibo experimental module, we have special device facilities to produce the artificial gravity for the small animal using centrifuge. And using that, that facility, researchers is focusing on how microgravity affects the human body. And this facility also provides not only Earth's gravity force, but also 1/6 lunar gravitational force. And currently, researchers are conducting experiment using the lunar gravity and determine the effect of human body. And also, as an astronaut, we have good relations with flight doctors, flight surgeons. When staying on orbit, we have weekly meetings, medical conferences with flight surgeons here. And also, if we have, normally astronauts are very healthy, but if there were any medical issues, the flight doctor would provide professional support through telemedicine system or guide us to treat the problem. And when it comes to the rocket launch or spacecraft return landing, they will provide very intensive care for astronauts, and their medical team provide rehabilitation program to help the adaptation process for the astronauts. And isolation and the confined environment. Personally, I didn't have any issue when I was living in the space station because ISS is very huge and plenty of room there. So if, let's say, if we have a personal conflict between crew members, but we can have a private space, isolated ourselves and cool down, then restart the relationship between crew members. And but that is not possible in the future exploration, like in the very small spacecraft or pressurized rover. Inside is very, very crowded like this. And there's no way to escape when there's the interpersonal conflict. So in that reason, astronauts are very well trained to cope with stressful situations, difficult situations. Even though it's the space flight is challenging, but we enjoy life in space like this and in a harmonious way. And it becomes almost a second nature for us to manage frustration in a positive manner. And this is a side story, but one unique feature of Japanese astronaut selection is they are using isolation chamber in the selection process and test the applicants in the space station-like situations. And from that point, that reason, Japanese astronauts are well prepared for the confined small environment. And the space food is my favorite topic, everybody's favorite topic. And thanks to the big help from the food companies and JAXA engineers, we have now more than 50 food products, Japanese food products, like curry, ramen. Unfortunately, we do not have sushi yet, but we have canned fish. And interestingly, the high school student developed the official certified space food, and now it's provided to the astronaut on board. And this is a great story, inspiring story, how space program educate and inspire younger generations. Another food topic is fresh food, like this, kimia with oranges, lemons. And the fresh food is a big morale-boosting item for astronauts, just like ryugu salad we ate last night. And when the cargo space vehicle, like HTB here, comes to the space station, there's always crew care package. And inside the crew care package, always fresh food. That's the bonus for astronauts. And with the help of local governmental organization and local farmers, we delivered, JAXA delivered for us fresh food like this to the space station. And these fresh food can be a special breed or can be treated in a special way so that it is kept fresh for a relatively long time. And this agricultural technology can be used on the ground as well as future exploration mission. And cross-cultural and multi-team system. By definition, the ISS is an international effort. And according to NASA, there were visitors to the ISS for more than 20 countries. And the training for the space flight is so long and so intensive so that when the rockets launched, the crew members became so close each other and become family or brothers, sisters. And the differences on the nationality or language or gender or professions became blur it's nonsense at that time, and only recognized, understand each other based on their personality and opinions. And that's one of the beauty of the space program, I think. And in the astronaut training, especially the focusing on the softer skills like leadership, teamwork, decision making, stress coping. These trainings are conducted in the field or in the mountain, snow, or underwater. And since the space flight is characterized as a multi-team system, so the usually in this kind of training, we invite flight controllers and flight surgeons as a crew member, as a part of team member and participants. And through the training process, we foster the mutual understanding. And on the same way, the astronauts on the ground, like me right now, usually work as a member of flight control teams. And most Japanese astronauts are certified as ISS communicators. And even in a unique case, the Onishi Takuya, he is my classmate. He has dual certification. He's a communicator and also as well as a flight director. So in the daily operations, sometimes, quite often, he leads the entire flight control team. And JAXA astronauts has a good reputation having a close tie with flight control team and mission managers. Maybe because we share the office space together due to the shortage of room in the Space Center. Maybe we are having too many parties together. But anyway, we got the organizational award as a model, the good cooperation between the crew member, flight control team, and the mission manager. Multiple times we awarded. And EVA, as you can see here, the future exploration is quite different from the mission on the ISS. The ISS, it is a laboratory, so lab, orbiting lab. So astronauts are working there inside, just like researchers working in the lab in every day. But on the other hand, for the lunar exploration, astronaut will work outside of the habitation module or pressurized module, pressurized rover, just like geologists searching for the samples on the field trips or excursions. In that sense, the EVA is more and more important in the future. And ever since the Takao Doi did the first Japanese spacewalk, all JAXA astronauts are very well trained for the extravehicular activity. Current JAXA astronauts are all certified EV crew members before going to space station, and often conducted the actual EVA whenever they are on board the space station. These skills and experience have been providing our knowledge and experience is useful for development of pressurized rover and gateway module in the future exploration. And the last one is science. Why do we go to space? Because science. Why do we go to the moon? Because of science. So this is the most important theme or goal for astronauts' activity. And because of the origin of Japan's manned space flight, we have a good relationship between academia and astronauts. And oftentimes we go to universities and institutes to see how experiments goes, and sometimes we got training from the principal investigators. So they come to reversely, they come to space station and help the operation on board the space station. And as ground astronauts on the ground, I support the principal investigator to conduct the experiment on board. And sometimes we have academic conference together and speak about the researches and about the space. And for the future lunar exploration, geology is also very, very important. And we have the geological field trip a couple of times with local geologists, or sometimes we go under the ground exploring inside the cave. I got the chance to see a lava tube in Arizona, or sometimes we go to the field to test the newly developed instruments or tools. That's also a great opportunity for us to prepare for the future exploration. And the last slide, we know our new destination is far away, but I can tell you that we have already started our steps forward, and I'd like to say let's go to the moon together. Thank you very much for the attention.
Thank you so much for that wonderful presentation. Every bit of it was fascinating. So congratulations. I know we're running just a little bit late, but nevertheless, would you be willing to take a question or two if anyone wanted to ask something? So any questions from the audience, please.
You infer that the harmony, astronauts are with harmony under the conflict. I think that's good. I want to give such ability to our students and our colleagues. So what is the secret, or how you obtain such a harmony? What is the technique? Tell us.
Well, we have a privilege to train together for a long time, working together. Even now I'm living in Japan. They are living foreign countries, Russia and US. But quite often we meet together as training sessions. And through these experience, we know each other very well and understand the nationality or differences are not so important. All we need is to know each other well, talk a lot, and maybe drink a lot. Then everything is fine.
Any other question? Okay, so thank you so much. So now we turn the podium over to Inetani Sensei and the panel on the session on the farther term future of the moon. Inetani Sensei.
Good afternoon. Thank you, Mr. Kanai, for a very wonderful presentation. After his presentation, could I have this? In the something wrong? Yes. On this session, I would like to introduce the activities, primarily here in our Japanese team, and for the Moon Village Evolution and the Reference Model team. And I was a little bit introducing what's going on. And after my introduction, we have original planning is 5 presentations for these studies. But unfortunately, one guy, on the third guy is Mr. Odan, who is taking care of the legal or societal activities. He has all over the sudden has suffered from a flu and very fever this morning. And he called me, he couldn't come. So that's the reason why I have a time for one slot. Then I was obliged to do this introduction, 10 minutes or something like that. So that's the reason why I have a time to introduce our activities a little bit for the assistance of our following presentations. Thank you very much indeed. Then, this kind of activities, the motivation is the reference model is some sort of the thinking or brain experiment to figure out how the societies are going on, how the society will be built, how it is operated, what value they could produce, what kind of business they can do that, how the society will be operated by, we need, let me say, the public service, such as clean up the road, policemen, fire extinguishing, code, things like that. That's a society, I mean. So in order to have such a society on the moon, what should be considered? That is a motivation. Then making a reference model as a quantitative manner, like how many people down there, how much money they can produce and things like that. This kind of a brain experiment, we did it. That's the motivation we have done it. Then the number of people is, yes, our existing space program, just crew member, of course, occupied by astronaut like Kanai-san. It's a very, very selected people. But in the society, I mean, it's not all is selected people. That's the general public, I mean. So how many people we can consider for this society members? That's maybe it is not 3 or 4 or 10 or things like that, but more than that is hundreds, thousands, 10,000 and millions, things like that, like a city or something like that. So to what extent we can take into account our consideration. And there's members of society. It's, let me say, this one is 100 people down there. We have firefighters and fishermen, and maybe one astronaut down there, but fishermen, and fire extinguishers, and the policemen, and many composition of the people should be existing inside the society. How it is operated. This is one of the idea to figure out, to be figured out. Then what kind of business we do, what kind of revenue sources we will take into account. This is a similar field on the Earth, making science, making tourism, making resort, making mining, or the making energy stuffs. Just how much let me say, revenues will be produced in order to take care of the society. So the space program is more than $100 billion program. We have to take care of that by making a revenue output. So what's the balance sheet in between? This kind of consideration should be made. So taking this into our consideration, we need an assumptions for the quantitative or qualitative analysis or consideration on that. Our assumption we took is, anyway, think about the large number of people, maybe, for example, the 1,000 people society. It's not very large, but not very small. But in comparison with the present space programs, it's a huge, tremendous number. So how do we take care of that? And then the assumptions of the 1,000 workers, just workers going 1 year working and come back to the Earth. That's assumption one. The second assumption is workers and his family stay down there and as making a life as a family. Growing children, maybe. People will die, born, things like that. And assumption C is a steady state society, which means birth rate, dying rate, and population pyramid type of consideration. We have to do that. That's the final image of the society, I mean. So taking these things into our consideration, our following presentations, people have thought about that. And then from now on, I will, yes. This one is the 5 working groups we composed, and for making the architecture considerations, business making considerations, and operating society, legal society. But I'm very sorry, the third one, today, he was suffered from the flu, and I'm very sorry we haven't him. And the fourth and the fifth, we have a scientist and people who did it. So then, after my introduction, this is my introduction, and following my introduction, starting from architecture consideration made by Professor Kitaya Sensei down here. Yes, starting from Kitaya Sensei. And Mamiya-san from Mitsubishi, yes. And I'm sorry, the third one is missing. Life Sciences and Izumi Sensei from Nippon University. And the third one, the last one, humanity and anthropological considerations from Okada Sensei from Kobe University. This is my introduction. Thank you very much. Onegaishimasu.
Okay, so I'm a top batter of the study group. So, as mentioned by Inatani Sensei, we have the 5 groups, and I'm mainly on architecture working group. And in this group, quantify the facilities, equipment, and transportation needed to build a sustainable human society on the moon. And also, how can we build a social management system using as much as of moon's resources, indigenous or in situ resources as possible. Okay, so there are the members in this working. So in this time, my name is Yoshiaki Kitaya from Osaka Metropolitan University, and I will talk about this matter in place of Dr. Sakamoto mentioned in the program. So why do we establish the Moon Village? The several purposes, and for working, sightseeing, and doing research, and satisfying curiosity. So what should we consider? So the functions, a number of people, living space and facilities, art, air, fuel production, and food production, and rigorous refining, and Earth-Moon transport. So this shows the overview of the Moon Village in the development stage. So we are intending to make the Moon Village with 1,000 habitants, and also the 10,000 visitors or sightseers from Earth per year. And maybe they will be staying in a residential area, sightseeing area, and the suburb area for some industrial area. And this shows the functions of number of people and the number of people required. So we have several functions. For example, circulation in infrastructure systems, urban infrastructure, and maybe resources and manufacturing, and maybe transportation, life services, etc. And maybe in the category of these functions or working categories, for example, we need around 700 people for maintaining the Moon Village, and also other people. And in total, around more than 800 people must be staying in the Moon Village. But this number must be reduced by reducing the maintenance staff. So this shows the residence system, living system. So we are now considering about how the 1,000 people can live in the moon, on the moon. So, for example, the Vatican City, the area is 0.44 square kilometers, and maybe around 800 people are living. So our intending Moon Village system, the area is 0.25 square kilometers, a half of the Vatican City. But the people must be staying living in at around 1,000. So we need to make the living facilities and other infrastructures. It's a quite challengeable items. And next, the evaluation of the cost of air and propellant on the moon. Propellant is the fuel. So, for example, if we produce the water on the moon, it costs about 2,000 yen per liter. And also oxygen, $10,000 per cubic meter, like that. So it costs quite a lot. So that maybe we must reduce the cost in near future. And the food production, this is my section. So how do we live on the moon? And maybe in the result, so one person can survive with 54 square meter culture area with sweet potato production can survive the people, many people, and maybe we can obtain enough food with nutrition and energy, And also we get the enough water by purifying of the plants. So for 10,000 people facility, we need to construct such kind of plant factories on the moon. So these system planning is based on the actual numerical experiment, not numerical, experiment, quantitative experiment. So maybe we calculated the 54 square meter per person culture area. If we culture the sweet potato, the leaves and also the sugarless roots can be eaten. And also the calculation is based on the actual plant factory system in our university. So that maybe the planning estimation is not so far away from the actual system. Maybe in our facility, in our university system, if we produce the sweet potato in a plant factory, so we can support the survival of approximately 150 people. And also, we need to obtain the protein, mainly from the animals. So we are now doing the research on aquaponics system, which with sweet potato and tilapia fish production and other kind of fish species. And maybe 80% of input nitrogen is accumulated in plants and 20% in fish. So we can efficiently recycle the, for example, nitrogen materials. And another aspect is the effective use of regolith. So we must use the regolith for construction or any other material production for human use. And maybe we skip the explanation, but maybe in such kind of system for converting the regolith to other materials, so it takes a lot of money and also a lot of electricity. So maybe the use of in situ resources is quite important. And the last aspect is transportation between the moon and Earth. This is quite important for transporting the materials from the Earth to the moon and also transport the human. And maybe even at the desired transport cost, the transport is quite large. So maybe we must reduce the cost also. And maybe the cost calculation is also done in the working, and maybe quite a large amount of money is required. So conclusion, the society of 100 permanent residents and maybe 10,000 tourists per year on the moon was considered in this working. And improving the feasibility and the efficiency of Moon Village would require the construction of labor-saving urban structure. And the cost of maintaining Moon Village is very high. So even under optimistic assumptions, and it's difficult to find a realistic solution at the moment. But we should find a better way, maybe in near future. So, and on the other hand, we believe that comfort is important, as a motivation for migration to the moon. And that the cross-sectional problem-solving method that bridge the gap between ideal and reality issues are quite important. That's all. Thank you very much for your kind attention.
Thank you very much, Professor Kitaya. So just one question from the floor. Is there? Yes? Is it okay? If there is, then please ask him personally. And he's a specialist on the space agriculture. Yeah, okay. But then, yes, that's a this collection of many technical disciplines and studies and activities. Yes, okay, thank you very much.
Thank you very much.
Next speaker is a very interesting one and for business making. And, oh. The business modeling of mining and the tourism, presented by Ise Mamiya from Mitsubishi Research Institute. Oh.
And Mr. Asazuma.
And Mr. Asazuma from iSpace.
He's
a very good friend of mine.
Thank you, sir. Okay, so actually for this part, I'm going to explain the first half, and then the second half, Mr. Mamiya is going to explain. And for this team, Mr. Mamiya and also Mr. Uchida, and me, and also Onuki-san is involving this project. And then we actually kind of focus on mining and tourism for this part, because we think, you know, the first business on the moon could be either both of one of them is coming at the beginning. And then as Iwatani Sensei explaining, we set as this kind of numbers, figures to start with. And then as iSpace is explaining, 2040, we have 1,000 residents and also 10,000 visitors every year. So we set that number, for assumptions. And then based on this discussion, we think the picture of the lunar business. And the objective for this working group is to see what's the future picture for this business. And then again, we mainly focus on mining and tourism market. Okay, and I'm going to explain the first part for the mining process. So you can see this picture. I would say 2030s or mid 2030, could be 2040, depends on how first we can go. But you can see the one astronaut in front of you. Maybe this could be Japanese astronaut, could be, or American astronaut. So, say what? Oh, Kanai-san, could be Kanai-san. With rover, which will be made by iSpace or any members here, could create this picture. So you can check maybe the one on the left-hand side. Do I have any pointer? Maybe not. So you can see the lander all the way back. So maybe we can refill that lander from the facility, and you can make the hydrogen and oxygen from this facility. And you can see certain place where you dig and get some regress, and then we can get those regress and convert to water and then also oxygen on this kind of timing. And then what we kind of approach, sorry for the small letters, but I can read. We try like two different story to figure out how much is the SRU market and also the market for mainly life support. So the first approach is this, and then what we tried here is try to figure out how much flights we will have from the Earth to the Moon, maybe Moon to Mars, and over that. And then second step on there, you have to figure out how much percentage is coming from the moon. So you don't have to get everything from the moon, but you will maybe define certain percentage for this step 2. And then third step, this is really important, how much is the price per kilo? And the previous presentation, there was some figures like a $2,000 per kilo. That's one of the number you can maybe memorize. But according to a lot, different research, it could be between 500 to could be up to 30,000. That's the kind of range you can consider. Then also you will figure out the mission to Mars, and then also you have to figure out how much weight you will consider. And a similar approach, but a little bit different for the life support. First, you have to think how many humans, the astronaut and tourist, will be on the moon for 20 years from now. And the second step, just calculate how much how much water and they're going to drink, and that's the second step. And also you figure out how much resource you're going to use for that. And times supply, ratio, how much ratio is going to get from the surface of the moon. And then again, I think for this step, step 4, we set it in between 10% to 50% from the moon. So I think the beginning of the habitation, maybe low ratio from the surface of the moon, and maybe during 30s, the end of 2030s, 40s, it could be around like a 50%. So then you can get like a kind of perfect circular system. And then I think this is my last slides for the first part. So it all depends on, well, I'm showing only for the life support, but as you can see, it all depends on how many human beings going to be on the moon. And I have two types different. One on the left, I set it like 1,000 people at 2040, and the cost is $500 per kilo. And the left one is 30,000 kilo, which is really, really expensive. But if you're going to bring water from the Earth to the moon, just imagine how much it's going to cost. So we set it as a kind of maximum amount for that point. And my last word from me is, well, you can see the unit. The one on the left, it's million, 10 million, 30 million, 40 million. And the one on the left, 3.5 billion, 40 billion. So what is this? If you talk to anyone on the moon, on the ground, hey, why don't you join? Why don't you build something on the moon? And that the market will be 4 billion, 3.5 billion. Well, some of the people on the Earth gonna say, oh, I'm gonna do it. But what if you said it's only 40 million? That's not big size. So it's all depends on the price per unit, and everybody think it has to be really cheap, right? However, if it's too cheap, nobody's gonna join to build the market. So that's a little bit vice versa. So it's just like one study for you to show the figures for the business market. So this is my last slides, and then hand to Mamiya-san, okay, for the tourism.
So thank you for Mr. Asazuma. So here I'm going to talk about the lunar tourism market. So we try to get the number of the market size or as annual revenue. So firstly, we planned the lunar package tour, and then to determine the price. And then we also estimated the annual visitors to the moon. And then we can get the annual revenues by multiplying the package price and the annual visitors. So here, first of all, this is our plan to lunar package tour. And you can, of course, enjoy the stay on the moon more than a week. And also you can get some kind of service before the launch, like health association, health maintaining or training. And after they come back from the moon, you can get also another support as aftercare. So we estimated the price was the $1 million in total. I think it's feasible compared with the like ISS or maybe the most expensive hotel. Not for me, but it's a not huge high number, I think. But we have to also consider the transportation cost from the Earth to Moon. Unfortunately, this is super high, very expensive. We estimated this cost is $100 million. We also think about this based on the real project, the moon, or maybe we also know the cost to the ISS. So we decided to consider the transportation cost as a total to a price. And we also think the two scenarios, nominal and optimistic. Optimistic means we can see the drastic cost reduction for transportation. So we can get a number as a total price per visitor in each phase and also each scenario. I forget to tell you that we think about the three phases. First is early phase, and then mid phase, and finally mature phase. Because situation is changing step by step, so we estimated in three phases. And we also estimated the annual visitors to the moon. Finally, it reaches 10,000 visitors to the moon, which is a given condition by the study group. So we set some number in each phase. And also we did consider the maximum capacity of the Starship. And they said Starship can fly with 100 passengers. So I think this is a limitation of the capability. And we also think about the mission, how often they go to the moon. So we get a number. And finally, we can get a number of annual revenue, so which means it is a tourism market size. So finally, $50 billion to $200 billion in the annual in 2040. So this is I think a huge number, but we can get just number. We are not sure about this. We need a more concrete, concise image. So we also compared this with other similar markets like space tourism and Antarctic tourism in 2040. So the inner red rectangular one, we estimated the size, lunar tourism, $50 billion to $200 billion in 2040. And also we know here, the space tourism would be $14 billion in 2040s, and also almost $1 billion for Antarctic tourism. So I think lunar tourism market size is slightly excessive. Also, we can know the whole entire space market. That was $400 billion last year. So even compare this, this number is, I think, just a little, slightly excessive. So which means maybe number of visitors in 2040s are too much, or maybe transportation cost is too much expensive, and even the condition that the 10,000 people visit the moon. So anyway, we can find out the two major market, what's going on the moon in 2040, and we studied two major markets, mining and tourism. And in the future, we need to refine this model because we didn't, complicate the math, just a rough consideration. And also, we have to apply this to other fields like transportation or communication. Thank you for listening.
Thank you very much. It's a very interesting and topic of money is a very understandable for an understandable measure for everybody. But a huge amount of money we need, but a huge amount of market we can expect. Yeah, that's a business consideration. Thank you very much. It's we are a little bit behind the time, and if there is just one question, or you can ask personally to both of them. Okay, thank you very much. So I'm very sorry to tell you the third guy, the Tetsuji Odan, is, as I told you, that he's in a serious fever this morning. He couldn't come, and I'm very sorry for that. And his study is very much interesting for the legal or the societal organization structure activities and things like that. But we will have another opportunity to tell you what's going on these activities. Then the fourth one is presented by Ryutaro Izumi, Nippon University, for the medical life science issues for society on the moon. He would like to insist on the medical rather than the life science, he told me, but he's also showed us very interesting stories in relation to the life science and the medical. Okay, Professor Izumi.
Thank you for Dr. Inatani. My name is Ryutaro Izumi, Nihon University. And there is only 3 persons, Dr. Ishioka and Dr. Takahashi, but many staff are contributing to this work. At first, I would like, sorry, that our university is very confusing, and I'm apologize to you. However, there are some activities in our university for space development. For example, the right side, Dr. Iwasaki is a president of aerospace medicine. So, the left side is Dr. Nomura, is president of microgravity. This is a time schedule of human moon development. Current program is Artemis. In this program, continuous human stay on moon will be materialized in 2040. Based on this concept, 100 person or 1,000 person on moon will be materialized 50 years or 100 years in future. I would like to talk my presentation based on this time schedule. As you know, space environment is very hard. There is no air, temperature is very high or low. So we could not live without closed environment. And there are problems of gravity, radiation, and magnetic field. Sorry, some words are Japanese. This is the effect of space environment for human physiology. Those medical issues and countermeasures are summarized on NASA Human Research Roadmap. This is a very reliable database. So we consider our program based on this database. Now, as you know, as I already talked to you, the society will materialize 50 years or 10 years in future. The technological development is very rapid in medical and life science field. So we should consider this point for considering in medical and life science issues. The first is artificial intelligence and robotics. As you know, the AI will exceed our ability in near future. To tell you the truth, I myself is medical doctor, but probably I will lose a job within 20 or 30 years. Many people will lose a job by the development of AI. The second development is several monitoring system, wearable or implant devices. There is no gold standard to estimate stress level of human, but combined these several parameters, we could estimate stress level as a whole. And the important point and also make countermeasure and treatment. And more important is this is not only personal level, including human society to monitor and management and control. This item is conflict with privacy. But in our society, we are already monitors our privacy by several devices and opportunity. So people do not worry about this point. Another technology is reading of mind. Also, this technology will be coming truth, not so far future. If once this technology is developed, there would be come to revolution of communication. The another technology is genetic engineering, clone or regenerate organ, and drug food will be synthesized by chemically. Also, life itself will be synthesized, not so future. The another technological development is superconductivity. In this research, in recent days, several items are reported. When superconductivity is materialized, there is a change of radiation. We could make a radiation shield by strong magnetic field. This may be materialized by lower level or personal level, but we should consider the effect for human or devices. The next development is anti-aging and artificial cold sleep. There are many medical items for in space, but we focus on five issues: cosmic radiation, psychology, gravity, moon dust, and transgeneration. Another topic, life in space, but this topic is very wide, so I hope this will be discussed in another working group. Entertainment and another entertainment. The final topic is next generation. In my personal impression, the pregnancy and birth is not so difficult, but most key important is human growth, especially in younger days. The effect of environmental factors such as gravity and radiation very sensitive to these younger people. So whether we could materialize next generation is a key point for this, how to cope with younger days. The next item is human evolution. Is moon society is a next step of our evolution. There are three ways to consider. The first is we ourselves create our next life, new human, or we ourselves will be evolved as individual base or society base. Dr. Sano talked about this topic yesterday, to move another habitable planet. This is Proxima Centauri B, 42 light years from the Earth, and it took 3,300 years to move. And this human will be evolved due to this experience. Several persons talked about evolution, human, and space. The most recent topic is this is a right book, Homo Deus, written by Yuval Noah Harari. This is human evolution. The final topic is why should we predict the future? Also, this topic was described some writers. Desirable human society or desirable technology. In my opinion, the predicting future is our responsibility as scientists. So this is the final slide. Ironically, I think We cannot live in space without controlling our planet, the Earth. Thank you for your attention.
Thank you very much. It's on time, and we have time for questions and discussions. Can I ask my question to you? The human can adapt the environment in space down there, or the question, those humans adapt themselves into the environment over there, can come back to the Earth, or it doesn't matter, come back to the Earth. For a long future, this kind of discussion should be made. So making a use of life sciences, they can solve this question, or both we can choose, or things like that, this kind of problem. This is not only for the bioscience question, but also to the anthropological questions too. So maybe Professor Okada will tell. No? Okay. Yeah, I'm very much in favor of this kind of discussion. Yeah. So to say something about from a life science point of view.
I have no idea.
Yeah, so they adapt ourselves into the environment down there, the low gravity, or the, let me say, the radio hazard and things like that. We can overcome technically, or we can overcome from a life science point of view. Just if there's a comment on that. So the life science can solve everything or not. Okay. Yes, please.
So, in terms of predicting the future, in terms of predicting the future, what is your prediction? When will the first human baby be born on the moon?
I think it's not so far. Probably 50 or 100 years in future. Only birth. But growth is different.
That's not my question. My opinion is it's much faster.
Yeah.
Maybe 25 years.
Okay.
It only takes 9 months.
Yeah.
Okay, so this life science issues are very much, let me say, the very interesting, of course, and very important for us, for our future. For example, the building society, not only for the working place and going back, but to stay down there, birth, death, growth, that's will be very much connected to the life science issues, to my understanding. So that's the reason why this point is very much important for making society point of view. This is my, thank you very much indeed. Yes. Okay. So the last speaker is Professor Hiroki Okada from Kobe University, the anthropological considerations for creating a society on the moon. Professor Okada is a famous professor for let me say, the cultural consideration, human being in space and things like that. Thank you very much. And okay, Professor Okada.
Thank you. Thank you, Mr. Chairman, Inatani Sensei. It is my honor to give a talk here, taking advantage of this opportunity. I'd like to thank program MBA committees and staff. My name is Hiroki Okada, Kobe University, culture anthropologist. So my presentation may differ slightly from majority of contents in this workshop. is focused on the natural science and the engineering research. It might even give the impression of a skit during the show. However, as human beings now realistically considering living in space, starting to the moon, I believe now it is the time that humanities and social science researchers must tackle this challenge. I will first talk about the background of this presentation, share with you anthropological research on space anthropology. While it might seem strange for anthropologists to explore space, the anthropological research on space dates back to early days, really. In the 70s, Polynesian researcher, anthropologist Ben Finney contributed to a NASA research project. And after, especially in the recent time, there has been many studies. Unfortunately, it seems that Japanese anthropologists have relatively little interest in space. It's pity. This presentation aims to explore the assumption of constructing 1,000 population villages on lunar surface. The challenge lies not only in designing the society, but also in conceptualizing any culture that would exist within Moon Village. It is absolutely important to consider two distinct dimensions of culture. Firstly, culture with uppercase letters refers to human culture in a comprehensive, long-term adaptive form, including biological adaptations. Secondly, cultures with lowercase, small character letters refers to local culture. In this context, cultures does not refer so-called high culture, such as arts, but rather include language and nonverbal communications, lifestyle, habit, unconscious bodily movements, values, norms. This is a unique adaptive system concerning the environment, distinguish humans from other animals and contribute to formation and sustainability of society. These cultures represent a regional short-term adaptation to the immediate environment. This presentation focuses on the second aspect of culture. This illustration may be familiar to everyone. It's an imaginative depiction of space colony created by NASA in the 60s. In this illustration, you can discern the influence of urban planning prevalent at the time. Indeed, similar suburban new towns have been constructed on Earth in various locations up to the present day. The underlying philosophy of such urban planning is rooted in functionality and efficiency. This is modernization and globalization. However, on the lunar surface, it is varied to reproduction of faithfully replicate today's world, supported by capitalist market system, modernization, and globalization. Here, I would focus on the positive aspect of the multicultural situation, inventing the possibility of a new culture or a new world. However, the multicultural situation in space may only bring negative aspect or issue, like as conflict between different cultures, or forced unification with standardization of culture in the process of power politics. At first, I would pose a provocative question. Can we secede from our Lebenswelt life world, considering social and cultural aspect? The Moon Village with its potential for cultural invention, holds some parallels to life on Earth. However, can we truly secede from the Earth's atmosphere within Moon Village or a space community? The crucial question is not about whether it is right or wrong, but rather about the possibility new culture emerging. This is hints on our imagination. Creating village and envisioning the image of a community. Should we transplant the living aspect species from Earth as they are, reproducing a replicated of miniature version on the lunar surface? Or should we faithfully reproduce the dynamics of local communities on Earth? Following this, the perspectives of reality versus ideal, utopia, and model become crucial. Following this, the perspective of reality versus ideal, utopia, and model become crucial is face conflict sometimes. There will be a possibility that new culture will be produced through a substituting for appropriation of today's our culture. In other words, jumping or relating of culture in a different way will occur in the process of competing hostility between different cultures. Here, let's consider the assumption societal and cultural adaptation and development over time at the community level. Broadly, we can divide it in three stages: short-term, reproduction of the community, replications of the functional organization and systems from Earth, integration human-machine interface, environmental control in space. And next, mid-term, structuring the community, systematization, development of unique social and cultural form within the space community, application of diverse societal and cultural aspects from us. And long-term, physical and psychological change, physiological adaptation to the environment and the emergence of diversity, restructuring towards the society and culture, incorporating diversity, human evolution. That is neo-Homo sapiens appeal. This is slide illustrates the process of change in residential pattern. And the first step, temporary residence, short-term temporary stay. And next, intergenerational alternating residence, medium term, accompanied B family. Third, intergenerational alternating residence, medium term, accompanied by, intergenerational long-term residence, reproduction, formation of the family, succession generations, and the continuity of the community based on the assumption of a 20-year generation cycle. It's a common sense of sociology and anthropology. One generation is 20 years. And here, let's focus on the short-term process of community formation. The community formation process may be envisioned as follows. First step, action groups 1, community infrastructure development team only group. Next, action group 2, single functional or occupational group, residentially with small group, from temporary to ongoing. And third step, action group 3, community coexistence, multiple functionally diverse small groups, supporting group or residentializations group. And after, expansion towards continuity beyond the generation. Community, formation of the complex living community with differentiated sections, absence of generational or family constrained village, and in this stage, 1,000 residents. Now, there is a fundamental question. What kind of culture will be embedded in the moon village? There may be three cultural types to consider. Reproduction of existing cultures on Earth. It's like a miniature or a replicant. And the next two, standardized new space culture. And three, diverse culture akin Creole culture. I will focus on type 3 because the space environment, unexplored by human race, provides an opportunity to create recognitions that form the bias of current cultures. The term Creole originates from individuals of European descent born in a colony. For example, when French settlers established colonies overseas, children born in those colonies and familiar with their parents' native land were called Creole, to distinguish them from children born in the settlers' homeland. Colonial context facilitated the mining people, fostering cultural blending that ultimately resulted in the formation of new identity and cultures. It's Edward Grayson's words. It's escape. The coexistence of different cultures will emerge in the moon village, giving rise to a multicultural scenario. Three types of multicultural scenario can be envisioned in the space era. One, multicultural situations through interaction with other cultures in the moon village. And the second step, multicultural situation produced by the recombination of cosmology and worldview. And the third step, multicultural situation produced by adaptation to the space environment. Among these, the third stage is particularly important. To acclimate to the harsh space environment, humans might undergo body transformation through biotechnology. Can we regard a human race and undergo such transformations as a distinct culture? Considering such situations, there is a possibility of inventing a human race whose adaptation to space surpasses our current imagination. Anthropological knowledge reveals numerous instances where the racial groups that adapted to severe natural environment developed distinctive cultures. The adjustments involved in bodily transformation hold the potential to invent a culture beyond our current imagination. Today, a crucial aspect here that globalization is eroding the ability of community and nation state to equate community or national identity with the identity of their people. Additionally, globalization poses a threat to local identity and cultural diversity as it strives to establish a system of standardization, generalization, and commodification. Once, why did people exceed the ocean and go to the new continent? There was will which asked for a new society and culture in the motif. In advance, and also in migration in the space, human beings could not ignore that there is an expectation for diversity and possibility such as Creole culture in space era. It is just a problem of cultural and anthropological topic, what kind of new culture is generated. I hope. In above mentioned discussion, as for the belief in the power of culture, I might be optimistic. The reason that I believe that is I'm a cultural anthropologist. Finally, let us present a epilogue of this presentation. Assuming that biological analogy, biodiversity, can be applied to the culture and society. If cultures and society lose diversity, they are likely to decline. Thank you very much.
Thank you very much, Professor Kada. It's yes, it's about on time, and we still have a time. Question. Yes, could you let me know that the Creole, but it's in the meaning of a Creole is to my understanding it's a little bit uncertain. The Creole is what does it mean? The Creole. Yes. Yeah. Distinct from children. Mm-hmm. This is some sort of a local culture, or? Mm-hmm. Mm-hmm. Mm-hmm.
Yeah, I think.
Okay, I have to study more. Yeah. So the diversity is important to me.
So well, in the space Creole culture, we've added our culture diversity on us. I hope.
Yeah. Any question? French guy? Any question?
Yes, indeed, it was a mix of culture from different continents.
Mm-hmm.
We have Europe, but we had also
Mm-hmm.
Africa, and they invented a new culture.
Mm-hmm.
And they also, maybe it's a model for us, they declared independence from France. So maybe also when we'll have 10,000 people on the moon,
mm-hmm.
we can create the Republic of the Moon.
Republic of the Moon, Kingdom of the Moon.
Oh, Kingdom is fine.
Yeah, okay. Today's my presentation is I will emphasize, of course, it is my personal impression. Most of the planning of moon village is sometimes reproduction of today's society, today's world on Earth. But it is okay, not okay. I ask you. Not culture, the system of, yeah.
Oh. Yes, that's also a problem too. Yeah. So yes, technology will solve. That's one thing. Yes. Yeah. From viewpoint of life science too, the technology will help. The evolution of technology is much quicker than the life science evolution. Yes. So anyway, many new vision and many new point of view will be provided by this kind of thinking about the society on the moon. So many diverse way of thinking, way of doing things, way of making management, things like that. So that's the reason why we are very much interested in to think about the society on the moon. This is my point. Yes. Okay, thank you very much. Okay, we have a little bit more than 10 minutes break before starting the next panel session. There's a preparation for that.
Yes.
Okay, thank you. So that next panel is by John. Yes, and Bernard Foen, Professor Miyamoto, and Professor Tsuda. Yes, please enjoy the panel.
If you have not answered the accommodation survey, please make sure to access and input it. So I have sent you all the access URL by email. Please make sure to confirm.
Thank you. As you like. So we're going to go ahead and get this panel started. I think we're missing one of our panelists, but I'm sure he'll be along in a moment. So we are closing on our target, and we will soon land at the end of this workshop and symposium here in Karashki. We want to talk a little bit in the next couple of panel discussions about what motivates, what limits, what stimulates, what leads to the development of humanity on the moon. And we're going to start out with a discussion among ourselves. I assume he'll be along in a moment. On the subject of science and human activity on the moon. So we're going to be a little bit far-ranging. We're going to talk about the science of the moon, i.e. the study of the moon itself. Oh, please.
I was lost in the video already.
Yeah. Please. We're already started. You could tell by the way I was talking. The science of the moon, i.e. geology and impact, history, and so on. Science on the moon, for example, the laboratory sciences, and science from the moon, the science of, for example, astronomy and Earth observations and solar studies of the sun, heliosciences. But first, I'd like to maybe offer each of our panelists an opportunity to introduce themselves. And if you have one or two slides that you'd like to show on this topic, to show them. But we have until 50 minutes after the hour. I think that's about 40 minutes. And we want to get back on schedule. It's one of my hallmarks is being on schedule. And so let me ask if you could introduce yourself and maybe say a few words relating to the topic, if possible, in about 5 minutes. And we'll begin on the far end with Yuichi-san from ISAS JAXA, who has probably the most fabulous job title here on the stage. Please.
Okay, yeah, thank you very much, and good afternoon. My name is Yuichi Tsuda, and I'm from ISAS JAXA, Japanese Science Institute. And first of all, let me confess that I am not a lunar guy. So I'm rather science beyond the moon guy, but I would like to contribute to this panel discussion from the engineering point of view of space exploration. So thank you for displaying this. So this is the slides I prepared. So as John introduced me, I was the one of the biggest work I did was the Hayabusa 2, project manager of Hayabusa 2, which is a sample return mission to the asteroid Ryugu, and that was returned to Earth with the 5.4 gram of a sample of the asteroid Ryugu 3 years ago. And what I wrote here is that so if human stays on the moon, how will the quality of science change beyond the unmanned science exploration? And my answer is that so I have lived in the space exploration community for 20 years, and what I felt is traditionally space missions strongly prefer fly as you plan, and they don't like something to change after you launch. But the asteroid, that's something we know only after we arrive there. So before we arrive there, before we arrive there, we have to design the spacecraft to do the exploration there. So there's a gap, engineering gap between in the scenario itself. But in the Hayabusa 2 case, that actually caused a very severe problem because before launch, this Hayabusa 2 capability is just 100-meter landing accuracy. But after arriving there, we found that we could not find such a safe place there. And we are obliged to find the 1 meter, just a 3 meter, plus minus a 3 meter, so 6 meter flat place. So that means that we are obliged to find the 1 meter accuracy landing capability for the spacecraft after launch. So, but what we did is that the adaptive team working. So based on that, we finally find a solution to refine the spacecraft software and the strategy for operation, and then we could solve the problem, and then we could finally achieve the 1 meter accuracy landing twice in the asteroid Ryugu. So from that, what I learned is that the in situ adaptability is really required for the challenging missions, like exploring to unknown world. But before that, probably many of you in this floor knows that because you're somehow scientists, those who know science know big room for creativity and ingenuity is essential for good science. So probably you all prefer fly as you like rather than fly as you plan. I don't mean scientists are lazy, but not like that, but fly as you plan, because fly as you like, because we do not know the world, the environment beforehand. That's an important point. And please go to the next slide. Yes, so this is my other experience. So when we evolve the most in the space exploration, my answer is not flying the nominal mission. So after completing the nominal mission and everything is successful, then we usually get the bonus, like mission extension. And in the Icarus, that's a solar cell demonstration mission. The nominal mission was just 6 months, but we were successful. And then after that, we had a 3-year bonus. There we had a lot of challenging mission to experiment in space. And also for the Hayabusa 2, after the returning to Earth, the spacecraft is still alive. So we plan to fly 10 years, additional 10 years to explore 2 additional asteroids after the Ryugu. And the spacecraft is now flying toward that. And there we are planning more and more challenging missions. So mission extension, in situ experiment, that's a very good opportunity as an engineer to evolve. So in that kind of things can happen if we realize the surface activity on the moon, because the teleoperation 360 million kilometers away, still we have this kind of we could have this kind of evolution by room for challenging. But what if we stay on the moon, then the human can only exert the creativity or ingenuity more. So that's my feeling. So in the other word, without going to moon, we cannot go beyond. That's my feeling. Okay, so I will stop from then, and I have another backup slides, but I will use that if I need later.
Okay.
Thank you.
Thank you. So so these are, I think, really useful. Maybe there's some in his back. Thank you, Richard. Thank you. Okay. So I think these are really interesting and useful observations with regard to the establishment of humanity on our moon, whether it's people or it's robotic systems. The idea that we will be able to adapt, to learn. Oh, thank you. Thank you. Oh, it's good. And to respond to the unexpected. I think a good word which is often used is serendipity. So the discovery that you did not plan to make and that surprises you, like the cosmic background radiation. So our next panelist is Miyamoto Sensei Hardy from Tokyo University. Please.
Thank you. Hi. My name is Hardy Miyamoto. My background is geology. I'm a scientist. I'm a planetary scientist. Fortunately, I'm involved in lots of space missions because we have good engineers in JAXA like Toda-san. And now I wanted to tell about the science advance is really important. And once science discovers something, then additional question follows. So science is always endless, and it is kind of driver of new science. When I was involved in Hayabusa mission, it was kind of dream to go to asteroid Itokawa to get some photos. Did pretty good remote sensing observation, and it was very, very exciting. Then we thought that we really need the sample, and engineers worked in an extremely great job and bring the sample back. Then we could analyze the sample and compare it to the meteorite. Finally found out that meteorites are actually a piece of asteroids. So we have lots of meteorites in the laboratory, so we can study meteorite again and again, and then we get some idea about asteroid a lot more clearer. Then we want to go to another asteroid, different type of asteroid by using Hayabusa to the sun led. And it was also extremely great experience for scientists. So we get the fantastic science data. Then we really need the sample. And this time it went pretty well because of the sun, and then got the sample and we analyzed that. Then we want to go something else too. So the science is always something like that. Let me explain a little bit about what planetary scientists think about science, maybe a little bit. So the goal of Earth and planetary science is something like this. We try to understand how the solar system is created, or how the planets are formed, and in which difference in evolutionary history did only Earth become a planet full of life. And in this kind of scenario, the moon is in a significant position. So this is why we are interested in lunar science. I don't go detail, but we don't really know. We have some idea of how the solar system formed, but studying, then we have another question. So we need to deepen the question. The formation of the origin of the moon, maybe you believe that the moon is formed as a result of giant impact of the Earth. That may be true, but based on that idea and studying again the remote sensing data, then we realize we have a little caveat of that hypothesis. So we need a little to deepen that science a little bit more. The same for the evolution of planetary bodies, we have some caveat. So the moon is the Rosetta Stone to understand why Earth is full of life. So for this reason, we really want to study the moon, and I am pretty sure if we study the moon by using a new spacecraft or maybe human and higher resolution of studies, then new science question arise, and we prefer to work together with other engineers, other scientists to deepen the science. So it is probably an endless cycle, and maybe that is the nature of human being. Thanks.
Thank you. So I think this confirms something that has been believed for many decades, and that is that the moon is central to our understanding of the Earth and the solar system. The impact record is crucial in understanding the early formation of the planets and the evolution of the early solar system. I will confess just a little 1 minute aside. When I was a young engineer at the Jet Propulsion Laboratory, the moon was irrelevant. It was dead, it was dry, all the work had been done, hundreds of kilos of samples were sitting around, nobody even was looking at them because why bother? And then in the last generation, the last 20 years, it's changed completely. And it's not just lunar scientists who care about the moon, it's the whole world. And that is a huge impact on what everyone is doing with regard to space science.
Let me add a little one thing.
Please.
After Apollo sample acquired, then a lot of people work on meteorites and Apollo sample, and then the new missions, a lot of new missions to the moon, and then we analyze this data, then we realize the importance of Apollo samples. Last month, one of our colleagues got the 10 gram of the Apollo 15 sample, and we got so excited to see that, and we are now analyzing that. So the new mission, a new understanding, really advanced science, then kind of new mode, new wave of science.
And new technology, and the new technology in the laboratory sciences.
Exactly.
So let's not keep our final panelist out of the conversation. Bernard Fung is famous for his long career in lunar science and lunar exploration planning. So please, Bernard.
Yeah, so I'm Bernard Fung. I've been working at the European Space Agency for about 25 years. Actually, I started as a theoretical physicist, and then I went into engineering, experimental physics, optics. I did my PhD in a sounding rocket experiment in solar physics we launched from White Sands. So I spent 1 year in the US, and then I left to study stars in an astronomical observatory in Chile. So I can talk a bit about science from the moon. And then, as a solar physicist, I organized a number of solar eclipses, and there was a moon passing in front of the sun. And suddenly, I became the moon expert. And there was a new mission that we were studying at the time, MOHO, and then Smart One, and they told me, you are going to take care of this first mission to the moon. So that's how I became a lunar scientist. But actually, the first activities that I was doing is looking at space from the moon. And so we'll come back to this. Yes. But clearly, a very important point, and I like your point about the moon as a Rosetta Stone. So to understand the processes that work in planetary bodies on the Earth, other bodies, it's also a cornerstone. Like you build a house, you need a cornerstone for the architecture to develop missions that are going to be sent in the solar system. And that's why even if it seems that in the public we stopped going to the moon, still we had this foundation of what we learned from Apollo, from Luna, from the lunar theoretician as well, and to understand better other planets. And then also we launched missions there. We had the Vietnam War, so the US didn't continue on the moon. But, and then we had this revival with new technologies, with new understanding. We see a new faces of the moon. So that's this point, science of the moon. And this we will do from a laboratory, but also doing extravehicular activities that will be conducted by rovers in the first phase, and then by human, assisted by rovers, assisted by Earth scientists from Earth also, because we will have a much more interaction between the whole science, engineering, even public, citizen science we can do even, from Earth. We can have thousands of people involved in guiding what the rovers and the astronauts will do. So geophysics, we put seismometer to measure the core of the moon. It's still a lot to measure. We have a seismic measurement from the Apollo time, but we'd like to have seismometer on each side of the moon, also on the far side, and then we can really understand the core and the evolution of the moon. Even constrain better the internal evolution and what was the condition when the moon was formed, also to inform what was the impact on Earth. Geochemistry also measuring the composition of samples. We found water in mantle samples from the moon, complete new discoveries from very old samples. So by using new techniques in the lab, we are going to learn. And then we are going to get new samples. So we need science to define, where to find them, what are the parts to explore, what traverses to do, and also to curate. And then we have to rely on the experience of our Hayabusa colleagues, and they are the only ones that retrieve extraterrestrial samples. Some of these samples also could be completely new. Yeah. So that's science.
It's a long introduction.
Yeah. So science. Science of the moon.
Let's go through the entire panel.
Science from the moon. So we have You said 5 minutes?
That was 10 minutes ago.
Oh, yeah. So science from the moon. We can talk about telescopes. So we made experiment about telescope observing the Earth, the planet, the sun, galaxies, the first age of the universe, cosmology. Science on the moon will come back a bit later, maybe in the discussion, learning how bacteria survive, how to grow plants, and also human health aspect. And what I would like later, but maybe topic of discussion, if you can discuss what precursor science mission we need, and knowledge gaps, and how to protect. This is more topic for discussion. And just pass 2 slides just for illustration. We'll have astronauts taking samples and then bringing them in the laboratory. Next slide. We will have a laboratory with various experiments to analyze those samples. We'll have also astrobiology facilities. And the last slide, we will do human health studies. Okay. Thank you. A lot of science to do.
Yeah. Okay. So, one of the topics we were speaking about before the panel got started, and Bernard alluded to it a moment ago with regard to the handling of samples in the laboratory sciences. One of the major questions is whether or not the laboratory sciences will in fact lead to more activities on the moon having to do with primary science. For example, the handling of samples from Mars, or the handling of samples from other wet bodies where there is a real prospect of organics and amino acids, maybe even long complex molecules. So I would like to go back to Yuichi Tsuda-sensei, and just ask you if you would maybe say a few words, reflect on the role of sample handling and planetary protection, and how it might influence the kinds of things that we need on the moon in order to do really first-class science relating to samples.
Okay, yes. Yes, the HyPSA-2 returned sample from extraterrestrial body. And so we built a facility in Japan where we are doing the curation facility. And the returning sample is far beyond the remote science exploration. So the mission, that kind of project involved much more community, academic community, beyond just space scientists. And also the analysis, the method of analysis, we can use the ground-based, very big, like microscopic analysis that cannot be on board a spacecraft. And actually, we only got the 5.4 gram, and 40%, 20% is now delivered to the worldwide academia, and they can handle the sample of the Ryugu by themselves. So in that way, we can expand our outcomes to worldwide academia. So that's a really big impact beyond just one space organization. And as in terms of planetary protection, that's a very difficult problem. In case of the Ryugu, it was actually dead celestial body. So, so based on the regulation in the planetary protection, it was deemed safe to go there and get back samples from that asteroid to the Earth. But I think I'm not the specialist of the moon, but I think the moon is in the same situation. Moon itself is safe because there should be no life.
Until now.
Until now, yes.
we are discussing changing, and we are discussing eventually having some special areas we protect. For instance, we have the polar region where we have organics.
Because the human activity on the surface on the lunar surface may increase the some kind of risk. I think that's a very different type of situation. Before that, we just think about the going to some celestial body and something, the problem in between Earth and other celestial body. But what if we have another activity on the moon, and for example, if we bring some sample not on the Earth but to the moon, and then take some risk to do a challenging experiment there, and then the astronauts or people on the moon, can they go back to the Earth safely or not? That's another type of problem.
Yeah. So,
for the
please, on this topic, because I have a new one I want to introduce to you.
This topic.
Okay.
For Hayabusa 2 sample, that he brought back, there are a couple of science papers appeared recently. One is led by Professor Tomogi Nakamura. He found that there's the really fresh asteroid sample, and compared to the similar type meteorites, it's different. So, if you bring something back on Earth, the Earth environment really contaminates the sample, and he observed a little contamination in this Earth environment. So having the fresh sample on the surface of the moon should be geochemically very reasonable, especially because of the vacuum and constant temperature condition. That is extremely good for the science purpose.
So I wanted to pose another question to you, Miyamoto-sensei, because of your comments earlier about the geology of the moon. So, and again, from my background, I used to be the sponsor of a program called SP100, the Space Nuclear Power Program 100 kilowatts, and with the vision of maybe a megawatt and outer planet probes and so on and on and on. Anyway, the key question posing to the planetary scientists at that time, this is several decades ago, was, so if we could give you 100 kilowatts or even a megawatt for outer planet science, what could you do? What would you do? And there, it was unimaginable to them because they were thinking about tens of watts, not tens of kilowatts or more. And I'm going to hypothesize that the same thing is probably true for lunar geology, because right now it's a big deal to have a little rover with 100 watts wandering around for a couple of weeks. And there's no thought of, well, what about the expedition into the lava tube to dig out, 10 meters down in the tube, or et cetera. So anyway, I'd like your thoughts on how the kinds of new capabilities that could change lunar science will come into the minds of the science community. Please.
Absolutely. I mean, one easy answer is we can utilize completely new technology, maybe it's very, very strong X-ray CT kind of scanning system or something. But even for traditional style of geological observation, a lot of power is essential because, like on the moon, especially if you go to the shadowed region or in the night, we have to shut down everything, or like it's almost impossible to keep the battery alive. Yeah, but we need continuous observation, like seismometer, as she said, like that is important, and also impacts, like the ARS body is essentially a very good experimental field for the continuous small impacts. So we want to do some experiment or observation, continuous observation of flux of the small particles onto the surface. But now we can, because the moon, every 1 month, we have this long period of the night. We can't survive, make the system survive. Also, the rover can rove around some smooth area, but there are lots of very, very interesting areas in the highland, rocky areas. So we may jump over the place, and we can imagine a lot of different style of doing traditional geology.
So, and I'm coming back to you. But in a twist, I want to make a twist.
A tough one. Yeah.
No, I want to make a twist. So what we have discussed is the potential value of the laboratory sciences. We discussed the potential revolution that comes from these new capabilities, from surface mobility, from high power systems, from, I will just put a word in your mouth, from very high bandwidth communication. But there is also a whole class of science, which Bernard alluded to in his introduction, which is the science from the moon. For example, the radio science on the moon. And all of these new capabilities, the high power systems, the motors, the batteries, the communications, all of them are going to make radio noise. So maybe you could just say a few words about
science from the
radio
moon.
science
Yeah,
and the balancing.
Yeah. So clearly, okay, I want to follow on this sample because I have two dreams. One dream, even I don't need 100 kilowatt for that. I want to go in the permanent shadow region and make a sample of 2 meters. Yeah. Because this could represent 1 billion years of deposition history. I could sample 100 comets, 1,000 carbon asteroids, and then I could measure what has happened. So this is one first dream. The second dream, I can go a bit deeper to go to a layer from the time where the Earth was bombarded so much that it has projected some sample on the moon. So you could have like a 100 micron layer.
Like the iridium layer.
But yes, and this could be from a time before life came on Earth. So I can have a sample of the early life. So that's one of my science dreams. And I think that possibly with advanced robotics and being smart and with humans, we could do that. But now, okay, how do we protect the science we can do for future generations? Let's take the example. So this shadowed region, we have to protect some. But also we want to observe the universe. So we have a unique place in the solar system, the quietest place. That's the far side of the moon. And because we don't have all this emission from Earth. And so we can use that to observe exoplanet exoplanets like the Earth or Jupiter. You can detect them. You can observe eventually the dark age of the universe, so when the universe didn't emit light, but only one line, which is the hydrogen line, and which is shifted in wavelengths so that it could be observable in the radio range. Then you can understand the early evolution of the universe, and also if you search for extraterrestrial intelligence, you could do it from the far side. So for this reason, we have ready to find a way to protect some areas on the far side from pollution, radio pollution, that could be brought by ourselves when we have all this infrastructure. So we have to find a way to define. There is some exactly antipodal where we could protect in a crater, and then have also some regulation that protect this area. So there is an IAEA cosmic group that is looking at that with Claudio Maccone. And, but we have many other type of science we have to preserve for the future, not destroy the object of science, because in the future, they will come with detectors which will be much more sensitive, so they should not measure just what we have polluted. So that's, at COSPAR, we are also looking at having different park area on the moon. So the South Pole, everybody wants to go there with humans, okay. Let's go to the South Pole with the peak of eternal light, with ice exploitation, human base. Some propose to reserve the North Pole for research, a bit like Antarctica now. No resource exploitation and research, and then so going step by step to protect not only the science, but also resources for the future.
So this is another very interesting topic, and one that is important to the Moon Village Association. And this, which Bernard alluded to, is the question of how to coordinate, how to not regulate but influence, how to make harmonious all of these diverse activities having to do with lunar development and human presence, preparing for future Mars missions, possibly handling samples from Mars or elsewhere, ambitious geology on the lunar surface, all of these things, and to make them harmonious. What is the right regulatory regime? Within the Moon Village Association, there's an organization called the GEXLA, which is the Global Expert Group on Sustainable Lunar Activities. But it's not a regulatory or an administrative body. It's really a discussion group which is hopefully it informs activities that are being done by others that would benefit from this kind of harmonization. And so let me just ask again, Yuichi-san, if you would please maybe just remark on, in your working internationally and working on these topics, what are your thoughts on how could we collectively do a better job on harmonizing science, lunar science, and all of our other ambitions having to do with the moon? Please.
Okay, yes. So, yes, to enhance the science activity or the human activity on the moon, we should not just look into the moon, because the space activity is not limited on the moon, as you know, and the presentation by Kanai-san in this afternoon, there are a lot of astronauts activity just around the low Earth orbit, but we learn a lot from there, and we learn a lot how to expand that or extend that to the activity beyond the lunar Earth, low Earth orbit. So in that way, we have to promote all the space development in parallel in parallel, and then the one outcomes is the lunar activity, and then the lunar activity can also contribute back to the entire space exploration. So actually, I have some slides about that. So could you present? Display the next page. And the next page. Yeah, okay, so if we focus on the space engineering, then, so, you know, the technique of the exploration evolved from just flyby the celestial body to orbiter, lander, and planetary sample return. And to go to the Luna, to the moon, we need a lander, but the lander itself is not sufficient. So the question is can't we do the surface exploration only after we successfully landed on the moon? Our answer is no, because we did landing on these asteroids. That's in a sense easier, somewhat easier than landing on the moon in terms of the orbital energy. But still, we learn a lot from there how to do the surface mobility before we actually landed many times on the moon. So in that way, we can learn a lot from the other field of exploration. And could you both go to next? Yes. So this is just focusing on the small body exploration for 2 decades. And there are many different type of asteroid exploration missions from different space agencies. Some are the sample return, some are just flyby, and some are planetary protection, and some are slightly focused on the planetary resource. And many of them are very successful, and we learn a lot from them on how to operate the system in the vicinity of the surface of the extraterrestrial celestial body, or something like that. And then we can get the feedback from that to apply to the surface activity on the moon. And then once activity on the moon evolve, then they can contribute to the other space science and so on. So in that way, if we can coordinate with a very more broader perspective, and not just focusing on the moon, and that will be more academic way of.
So that's an excellent point. The idea that lunar science is inherently a part of the larger endeavor of human space exploration and space science, and that the techniques and the technologies and capabilities developed for one come back to the other and reverberate to the benefit of both. Yeah, that's an excellent point.
I have a short song about it.
Wait.
Just one. It's called.
No, really short. All right, take your mic.
It's called Fly Me to the Moons.
Yeah.
You go to Phobos, and then you go to the moons of Jupiter and Saturn.
Yeah.
And we learn a lot from the technology we develop on the moon.
Okay, very good. I thought you were going to sing. I was worried.
Well, I can play with the piano.
No, it's okay. So, but I still want to come back to the original point that I raised, which has to do with how do we orchestrate? How do we coordinate all? I accept easily, and of course, the point that you made. But I want to maybe ask Miyamoto Sensei about this, the other topic, which is sort of how do we coordinate across the sciences, across the other activities that we might do on the moon, that we will do on the moon.
Right.
Please.
Yeah, it reminds me when we discussed about Mars exploration in the past, we developed a life detector which may work on the surface of Mars. And at that time, we saw that the current environment of Mars, it can host potentially some life forms, some germs, We may find Mars life, but the criticism exists. That one may have brought to the surface of Mars by Viking or other previous landing mission. We cannot really distinguish them. So if once the surface of Mars is contaminated by terrestrial life, then we cannot really determine if the Mars originated life exists or not. So the one small things may affect something in different way. This can happen in the planetary scale. Given that, I reminded that the history of human weapon versus human culture thing, like the technology. In the past, we only have some knife, so a crazy guy can kill 1 or 2. But when you develop the gun, the crazy guy can kill like 10, 100 of people. The big bomb then can kill like 10,000 people, atomic bomb, a lot more. So technological advance increase the chances of destroying a lot of things. If the human beings' technology advanced far, far beyond, maybe we have some sort of like a planet weapon or something. Some stupid guy may use it, and I had the story that might be the end of it.
It's a little far afield from our topic.
Okay. Yeah. The point is,
I understand the concept, but it's a little far afield for our topic.
The point is, the technological advance should be accompanied with the cultural advance as well. So maybe the law or maybe the philosophy, or the other fields should advance at the same time. That's what I want to say.
Okay, thank you. So we are just about out of time.
Oh.
It's gone really quickly. I would be a scoundrel if I did not give an opportunity to Bernard to basically
Science on the moon.
Any comment you wish.
Yeah.
But 2 minutes.
Oh, 2 minutes. And
For sure.
And counting. So I would like then to end with science on the moon, because that's also a very important topic. Planetary protection, luckily, the moon, we can go with life. And luckily, we are not able to have military activities, and to bomb the moon, weapons of mass destruction are forbidden. So we can do peaceful science activities with life science, learning how organisms survive on the moon. So we have launched some experiments to space station. We are going to put them on the moon, looking how to grow plants, looking also human health. That's a very important aspect of science. And this is an area where you don't do it only for scientists. You do it because there are knowledge gaps that will help to define what we do at large scale. So you need to pay the scientist, so get me some PhD money so that I can pay scientists to help develop all the rest of the activities for the Moon Village. And human health includes all aspects, physiology, maybe also psychology, how we work as a society, governance, and so on. It's a science in itself. And we will also have to look at, okay, how are we going to have babies on the moon? And a society there.
Thank you. So I reserve to myself the last word. I will just say that I hope you have gotten from this very brief discussion a taste of the role of science, the importance of science, both in leading to and pursuing the extension of humanity to the moon. I will just say that in the coming couple of years, this is going to be much more an activity that the Moon Village Association pursues and looks at all of its activities through the lens of science on the moon, and in addition to, of course, commerce on the moon, which is the subject of the next panel, which Onuki-san Misuzu will be chairing. So thank you so much, and please give our panelists a warm thank you.
So, almost time. So, can I have your attention, please? Sit down, please. So, we are going to have the last panel today, and titled "How to Promote Commercial Activities on the Moon." So, you can see we have lots of panelists. So panelist 1, Taro Asazuma, iSpace. Panelist 2, Eric Zhang from DoraHacks. Panelist 3 is Hirokazu Mori, Blue Abyss, the second phase.
Right.
And the third panelist is Hirokazu Mori, and the next one is Ryuhei Takahashi from Arcade Space. And Satoru Cross from Yokogawa Electric. And Alejandro Sela from Geopos. And the last one is Maya Abe from ASE Labs. So, and first of all, at most 5 minutes presentation from all of the panelists, and then we will discuss.
Hey, good afternoon. This is Taro Asazuma again. And then this time I'll spend 3 to 5 minutes to introduce myself and my company. But fortunately, maybe everybody knows iSpace for in this room. So I'm going to spend just a minute to my company's figures, but everybody knows. So, and also by myself on the screen. But when you're reading, I'm going to use this time to give our gift according to what you put on the business card on the box. And then the gift itself will be this mug, this on sale, the one we use this gift for our landing timing. So this is like a limited 300. So I have 3 of them, and I know a lot of members left already. So I pick 3 cards, and if someone's here, I'll give it to you here, and then I'll spend 3 minutes. Okay. So the first card, dun. Mr. Takeda Kenichiro from Takasago. I think there left crap. All right, Takasago-san, Takeda-san. I'm gonna mail to him. Okay, the next one. Done. Miss Hirasawa Kihoko-san from Toray Research Center. I think they might be in the different room. Okay, I'm gonna give it to her. Okay, last one. All right. Oh, like a look. Mr. Ono. From I think he's in the other room. Okay, so then maybe you read my letters. So basically, I'm a manager of a partnership acceleration group and try to get the sponsors and for our mission. So that's my time. Thank you.
Is there a folder somewhere? Okay, so great to be here again, and as a person who doesn't have a business card, I will start my presentation. So it's great to be here again, and so today I'll be introducing DoraHacks and our initiative to support the open source community globally and foster space innovation. So DoraHacks is actually not a new organization.
we established the company and the community in 2014, and it has been almost 9 years. So what we're doing is we organize hackathons globally, and we also provide a platform that offers necessary tools for hackathon organizers, open source developers, and communities and organizations to host their own hackathons. So the goal is to connect hackers and open source developers around the world, and let everyone build product freely from the grassroots perspective. And so currently, DoraHacks is one of the most active platforms as a hackathon organizer and the community, since it's empowering a global hacker movement in Web3 and frontier tech. So far, over the past years, we have been distributing more than $40 million to more than 6,100 developer teams. And the platform is hosting more than 100,000 active developers and hackathon hackers. So the platform offers a few features. The first one is, of course, hackathons. We have hundreds of hackathons on the platform. As a developer, you can participate. As the organizer, you can organize your own hackathons. It also has grants for developer incentivization, community governance mechanisms like quadratic funding, MACI, bounties, and recently we added the new feature letting AI to generate startup ideas so that people can get inspired. And currently, we have two relevant events on the platform. The first event is a mini grant called Space Resource and Exploration Grant. It has been ongoing for more than half a year. So there are multiple tracks. So if some team wants to get supported for some proof of concept ideas, they can do so by applying for this mini grant. So far, we have 8 grantees. From information platforms to hardware, software developers to small satellite builders. And the second event is the Starship Use Case Hackathon. So this is probably the first Starship Hackathon ever organized, even before Starship itself is successful. So the way this hackathon is organized is that we provided 20 use cases. There are 18 specific use cases and 2 open challenges. And teams can submit to any of these challenges and participate in this hackathon. In addition to that, the hackathon, as an organizer, we also provide a list of hacker resources so that for people who are new to the industry, they can use these resources to learn and to build. Lastly, I want to mention that we have a Dora Dojo community. We are constantly inviting people from NASA, as well as commercial institutions and startups to share the latest developments and the newest ideas in the industry. So some useful links. Feel free to follow DoraHacks and join our community. Thank you.
So I hope I don't get any issues with my slide this time. So this is the second phase out of 8 I've got. You probably remember I made warp speed presentation with warp space, which was laser communication yesterday. And today I'm basically co-founder and the VP of a company called Blue Abyss, which is a UK-based company offering a human space service, which is still startup. We established around 7 years ago. It was a bit dormant, but it reactivated kind of last year. What we offer is basically like NBO. If you are in human space sector, you probably know Neutrally Buoyancy Lab in Houston, which lot of instructors conduct EVA training for astronauts. Usually like a professional divers provide the service. By the way, I used to be also a professional diver doing a lot of rec and a lot of research diving as well. That's why I found some of the co-founders as well. Some of the key points are on the left top area. Our pool is 50 meters deep with multi-level, and it's volume-wise, it's twice as big as NBL, which means we can accommodate bigger space stations such as Gateway. And the second point is we also have like a cross-sector integrated test facilities on their kind. We do work with several institutions in Europe to conduct some sports science, etc. And we do have some ESA heritage. Our CTO is Simon Ebbett, who used to lead some of the astrophysiology stuff in ESA. And not just pool, we're gonna have long arm centrifuge, which is usually used for G test, and also parabolic flight. This is not our asset, but we partner with Zero G company, Zero G Flight, in order to test, like 20, 30 second microgravity environment and stuff. And since we are a commercial company, we do plan to do some R&D lab. We are gonna run some of the R&D lab, not just for space industry, also for maritime sector as well. And we want to adopt some of the entertainment bit in order to make more revenue, right? Which also contribute for cheaper astronaut training service as well. And this is basically the overview. Our first facility is planned to be built in the UK. I'm gonna talk more about the second facility. We also will have a second office in the US, in Ohio, just close to Glenn Space Center. You may have, if you're from US, you may have heard of this news, but we purchased the ground, and we are also doing some base construction down there. And if you're also aware, some of the commercial space station companies are doing some activities there. That's one of the reasons we decided to base in Ohio. This is some of the specifications of our pool. As I mentioned, the volume-wise is actually twice as big as NBL, NASA's pool. And also the depth is 50 meters deep, which is considerably actually deeper than NBL. Actually, depth isn't so important for space use cases, but for maritime equipment test, depth is also important. That's why we have several multi-level structure in order to use it for not just for space, but also for maritime use case, in order to basically reduce fixed cost. We can control some new parameters which NBL cannot. For example, lighting, salinity, and also current. This is actually a big thing, not for space, but for maritime use cases. There are not so many facilities which can control current. We are gonna have those functions. I'm gonna skip this bit, and this is probably more important for people in the audience here. We have several, which is not, what's written there is not confirmed, but we are trying to basically optimize our facility even for like Artemis plan. In order to do so, basically preparing the underwater environment closer to some lunar or Mars environment, which also includes color as well. We talked with several people from ESA, NASA. Also, color of atmosphere affect our psychology. If you keep seeing the red light, people become kind of aggressive. You probably heard, if you look at the blue lights, the crime rate usually goes down. That actually happens with the red light, opposite effect. That we can also test those as well, and then we can test your brain waves in order to basically test and affect how, depending on what activity you do, we can also test what's going to happen before people go to Moon or Mars. Right? And there are several MOUs or LOI we collected. Those are the basically companies we got LOIs or MOUs. We cannot mention what we do with them, but one thing we can mention is with Jacob, we are doing some activity in the Middle East as well, but main activity usually happening in the UK or US, especially around Ohio. This is basically summary. We work with basically space, but also maritime use cases and subsea technologies. There are several already existing clients we are working with, and submarine technologies could be tested. And usually TRL 426 is the hotspot for our facility. People are looking for those facilities, but they couldn't find, and we are trying to provide those basically capabilities for not only for space, but maritime use case as well. Right, this is basically the location. We actually have one headquarters in Cornwall. We have second office in Ohio. We plan to have office in Middle East and Japan as well. That's basically it. I'm happy to mingle with other panelists. Thank you.
Good afternoon, ladies and gentlemen. I'm Ryohei Takahashi from Arcade Space. I'm a CTO of this company. So I'd like to introduce the Arcade Space. Arcade Space is a Japanese small satellite developer and space service provider, led by the CEO Takayoshi Fukuyo. Today, CEO Takayoshi Fukuyo will attend, has planned to attend this presentation, but he's busy, so on the behalf of him, I attend this. The current discussion. So our main focus is developing the CubeSat, the small size of the satellites, such as the shape is like the desk, shelf. So it's like several centimeter or several tens centimeters. And actually, I was a developer of the CubeSat when I was the graduate student in the University of Tokyo. So actually, I was the ADCS engineer of the ECLES, which is a 6U CubeSat for exploring the moon. And I learned a lot of difficulties to develop the satellite. And then after that, I joined this company to expand the more service based on these technologies. So until now, our company launched several CubeSats, such as LowerSat for education of the African country, and also the Optimal One, which is a demonstration of the IoT technologies. And also we join in several operations of CubeSats, such as the ECLES, which I developed in, and also which is developed by the Sony and the University of Tokyo, and we offer the operation support. And also, currently we have some projects to develop several CubeSat or small satellites, such as the VDES, which is a new maritime communication systems, and also OnlineSat for Taiwan Space Agency to monitor the Earth. Also, we got a project to explore the comet, which is called the Comet Interceptor, and which is more than 18U. It's more larger than the previous satellites. And our technology is based on my graduate university, so the University of Tokyo Intelligent Space Systems Laboratory. So this university has a history to develop several CubeSat, or world's first CubeSat, or microsatellites. So based on under the cooperation of this university, we developed the more advanced satellites. So our satellites has a modular design to efficiently develop the satellites for various applications, such as Earth observations, or maritime communications, or deep space explorations. And so based on the modularity or the efficiency to develop satellites, we have a long-tail model. So we plan to apply our satellites to various applications, such as the IoT education or Earth observation by using the spectrum camera, or maritime communication, such as the VDES project, and also the more deep space applications, such as lunar infrastructure or moon navigation. So our business is not only focused on Japan, but also we expand our customers, such as Brazil or Southeast Asia or African countries. So we have various missions to develop satellites, and also we have planned to launch many satellites. So yeah, actually, we got the project of the VDES, which plan to launch the more than several tens satellites. But yeah, we plan to launch more and more. And for lunar applications, actually, we have some experience. One is, as I said, we joined the operation of the ECLES, explore the moon, and we succeeded to take a photo behind of the moon. So we succeeded to operate or change the orbit by using the water propulsions. And also, we have a project to design the lunar navigations by using the small satellites. So as you know, to launch the many satellites to the moon, it requires many launch opportunity. But small satellites has a merit of the easiest of the launch because it has a very small masses. So we consider that it's difficult. We can apply our satellites to these applications. So and also we have a project on the deep space exploration, and also we developed our ground station to operate more satellites. So I think that for lunar navigation systems, it's important to maintain the ground station also. So actually we keep such abilities. So this is our companies. Thank you for listening.
Okay, so my name is Satoru Cross. I am the founder and also executive mentor of Space Business Development Office of Yokoga Electric Corporation. So Yokoga's history of space actually started back in 1961 when we supplied ion cell sensor to the former JAXA organization. And in 1962, we supplied the same sensor to NASA. So even though we started early, but we did the space as a project-by-project basis, and we are actually non-space company, which is diversing in space now. And our main business is a process automation, and technology is a measurement, control, and information. We have a bunch of sensors, controller, and also the information technology. So this is the most important slide for me. We are the automation company, so we supply our sensors to the many, the very extreme environment on the Earth, like deep sea and Arctic. So then naturally we thought our next horizon is space, but we didn't know how to enter that. We searched the market and we found that we can encounter a good book, Blast Off of Space Business, written by Mrs. Onuki. So in this book, I saw the one important introduction of an interesting university called International Space University in France. And then I went there back in April 2019. And at that time, like SpaceX just succeeded to get the 3 boosters back from Falcon Heavy. And in this week, the Israelis, the classmate, had a live stream to have the attempt of the first private lander to the moon, Belseed. It was not successful. So I was very much shocked positively, and then came back that this is the area of privatization or shifting a business from the national agency to the private company. So immediately after I came back from the ISU, I created the task force to start the space business as a part-time basis, and got some project from JAXA and METI, and then we decided to create the permanent organization back in July 2021. So in addition to Moon, so we have been doing several other applications, like we supply a payload to the ISS for a life science experiment, And we have been developing several remote sensing technology and some joint development with JAXA and so on. So why Moon? So as I said, we are an automation company. We are very good at handling real-time information and control everything, like the oil and gas plant, the pharmaceutical, and iron steel, you name that. So all the technology we have can be applied to the Moon. And so Moon has a land, and also we found water. So this is, we say this is the closest potential industry location to the Earth in space. And then after we developed the technology, we found that the new technology developed there, like the clean hydrogen-based energy supply chain, and some recycle circular system can be also beneficial to solve the problems on the Earth. So we are now excited to approach the Moon and get some technology and insight back to the Earth. So it's a busy slide. I don't tell everything, but we cannot do everything by ourselves. So that we need partners, starting from the research study led by Mitsubishi Research Institute. And then in this group, we met the iSpace people, and so we started the joint development about the Lunar Water Explorer. And then iSpace kindly involved the academia, like Miyamoto Sensei from University of Tokyo, Ibaraki University, and the Chiyoda Corporation is a system integrator. So we demonstrated the machine with drill. And then, so I also was much involved in the Moon Village Association, and also I made a presentation in the last session in Los Angeles. And Tuesday this week, so we made another the press release together with JGC to develop the control system and plan first time with let's say 6 seconds of latency, very much remote and very challenging communication. So under the Ministry of Economy and Trade and Industry, we are now doing a kind of study together with the partners to create the clean hydrogen-based supply chain. And these are the orange boxes are Yokoga Technologies, and we start from the Water Explorer. So I hope you had a chance to see our demo because it's already packed and shipping back to Tokyo. Okay, so we have a technology of the measurement, control, information. So this core technology can be utilized for the space on the Moon. So and also the creator the new technology, and this technology can be beneficial to solve the problem of the Moon. So let's work together to create lunar industries. Thank you very much.
Hello, everybody. My name is Alejandro Sela. I am the CEO of JOps. First of all, I would like to thank the organizers of this marvelous event and the MBA for hosting us and for letting us introduce our company. Operations. Operations is actually the forgotten discipline. Normally, operations come at the end of the mission, of the preparation of the mission. And this is becoming a problem now because the number of satellites, the number of rovers, the number of landers is increasing. And the number of operators, it's not. It is very difficult to find operators. You can ask all the small startups working here. They're probably struggling to find the operators on the market. This is actually from our friends iSpace. Sorry to borrow the picture. Yes. The problem is that also in terms of tools, the tools that are available in the market are outdated or extremely expensive because they were meant for missions much bigger than what we are doing now. Normally what is happening is that new space companies start developing their activities, and when they reach to the point of preparing operations, they think that they can just take one system engineer and put him as an operator. And this is like asking an engineer to fly an airplane. It's something that is a huge risk from our point of view. What they also do is to start developing their own tools. So since the market is not offering what they need, they start developing everything from scratch. So from the planning tool, the mission control tools, the shift planning, the voice over IP loops, everything has to be developed from scratch because the market is not offering them what they need. And what happens is that all this can lead to failures. And sometimes we are not very honest on why things happen. Sometimes we are, like iSpace shared their knowledge and the know-how. But we don't see everything that is happening on the satellites normally. But many times, one of the big problems is coming from the fact that the preparation of the operations were not integrated in the early phases of the mission or were not performed by trained people. So our idea is that this should change. The value proposition of JOps, and let me tell you that my team has people with experience in Earth observation, landing, rover activities, and International Space Station activities. Our idea is to bring the standards and the know-how from all this background and to create tools and the processes that are required to perform space operations. We are also very involved on simulation and test activities. We work with rover simulation tools, and we have our own tools that are ready to be used. And we also want to provide, on top of these tools, consulting, training and certification activities for all those companies that want to start and enter into the market to be able to prepare their teams for the challenging activities of the mission. To tell you also something interesting, I have lived many failures that were catch thanks to the preparation and the activities done by the operators. Even in the early phase, in the past, in the International Space Station, operations team were not really involved on the early phases of the mission. Actually, now we were, when I was working for International Space Station, involved almost on the PDR phases because there we can start telling you guys what is required for a mission to succeed. So that's why it's really important to bring this topic to everybody so that you never fly alone. I think that's the most important thing is that there is people like ourselves that are ready to support you and to give you the tools and the experience we have to share it with you so that you can make your mission a success. Thank you very much.
Okay, hello. I'm very honored to be here with great moderator Ms. Onuki and other panelists who are senior persons in space industries. And my name is Maya Abe, and I'm majoring aerospace engineering at university. And sometimes I'm doing a software engineer at small satellites, and sometimes a space business person. And I'm the founder and president of an organization called ACE Lab. ACE Lab is not a company. ACE Lab is a community that connects university students who have interest about space-related things and is developing human resources for a new era of space development through voluntary study groups. Through We Are Japan community, we has close to 300 students in community and from 7 different countries participating in space-related studies. These are our activities, and I will present the details of each activity on the following slides. First activity is study groups in our community. Study groups are the main activity of ACE Lab. And the study group meets once a week to teach each other based on technical books and papers. And with each member in charge of a particular topic, and the activities are held on an online basis, so students from all over Japan and around the world will be able to participate in. And topics range not only from typical space engineering topic or space science topic, but also from range to like fundamental engineering or space applied topics like computer engineering, embedded systems, and food production, international collaboration, business, or space law. Through these study groups, students create a number of study slides and videos. And some of such materials with high public value and return to the outside in the form of workshop or some websites and so on. And beyond the reuse of these materials, some members organize entirely new projects. Here are 3 examples. The first is a project that aims to produce flight-level small satellite components and open source it. The second project is a collaboration between American and Japanese university students to create Mars rover. And the third one is designing commercialized electrical power infrastructure on the moon. All of their projects are non-profit, but they are challenging themselves day by day to bring some kind of innovation to society by making the most of their position and expertise as students. These are the most significant results of planning and sustaining a study group that is completely led by students themselves. And to support these activities and provide the better experience for community members, our ACE Labs management team interviews space industry executives and engineers and published a survey report on human resource issues in the space industries and student altitudes. The report is scheduled to be published in February next year. This is some example pages. These are our activities in ACE Lab. In the future, the development of human resources will be an increasingly important issue in space development. In this context, a continuous cycle of training and providing human resources will become increasingly important. ACE Lab aims to create such an ecosystem, and in order to expand the space industry many times over, we'd like to ask for the companies and researchers and everyone here. Let's make the space industry a major global industry and reach our hand to the moon. Thank you.
So now, just before we move to the discussion, and short presentation from me. Space transformation. So the economic and social transformation brought about by activities on the frontier of space, so-called space transformation, is becoming a global trend. So as you know, space economy in the world has been dramatically increased, expanding, and expecting to expand and from now on too. Space is a marketplace, not only near Earth and LEO, low Earth orbit, even the Moon and Mars. Developed by more than 12,000 companies in the world, including more than 3,000 space venture companies. Regarding to the space moon market, more than 250 missions is planned or will be planned over 10 years, and which is more than 100 billion moon economy. So now, this panel is the economic side of the moon development, moon economic development. So now discussion start, and time is short. So 1 and 2 is combining. Opportunities and challenges for your activities and business is the first. Hi, Asazuma-san.
Hello,
Okay, in 10 seconds I can answer. Okay, as iSpace, opportunities, we have a customer, we have several customers, but challenge is we need customer's customer. Then the market will grow. That's my 10 seconds answer.
Thank you.
Next one.
Okay, I'll try 20 seconds. So from our perspective, we come from a different field. So we want to see more grassroots innovation and more from the open source hackathon community side. So funding and supporting these initiatives will be important. As Prime Minister Kishida mentioned a few months ago, the Web3 industry was a new form of capitalism. So probably we need new form of capitalism to fund the new frontier of space.
Right, I'm going to try 30 seconds. Well, opportunity-wise, so since we are like a human space training company, as you know, like a moon village vision, those are becoming more realistic thanks to Artemis brand and also the competition between two nations. That definitely we are seeing more demand from the government since last year. But challenges, it's very cost demanding in a way. It's like 3-digit millions. It's kind of the start. It's like same as rocket. So we've been struggling to raise enough fund, but we are getting there soon. So that's the status, I would say.
Okay, so my opinion is that the opportunity is the connection between the company or the space agency. So like iSpace, yeah, we can launch satellites. So it's very nice opportunity for us. But the challenge is that the uncertainty. So like the environment of the moon is not sure. Like, yeah, the receiving the GNSS signal is not sure country. So it is a challenge. So the phased approach, like the gradually expanding the economy is important, I think. That's all.
Right. For me, opportunity is unlimited. Unlimited, because there's nothing, no infrastructure in the infrastructure on the moon. So to create is all the opportunities. So challenges is just one, the time to get the return on investment. Thank you.
So for us, opportunity is the current expansion of the market. Is very hard for everybody to catch up with the evolution, and we are there to provide with some advantage. We work with open source tools, so price is also a good option for us. And then the challenge is what I just explained before, the knowledge of the decision makers about operations in the new space market might be a little bit reduced. I guess that the more they operate, the more they will realize that these kind of tools and this kind of investment will have a return. So yeah, thank you.
And from university student community, there are more and more students getting interested in moon development and space engineering or space development. So this could be opportunity, but we don't know more detailed information or environment in lunar surface or lunar orbit. So we require more high-level technologies or high level of knowledge. So it is very difficult to enhance our technology, and it is very difficult to grow human resources. So growing human resources and engineer or some other supported positions could be a challenge for us, I think.
Now we have more 10 minutes, plus 10 minutes, so 15 minutes total. So the next one is a moon economy. Moon economy means a moon and industry, or what is moon industry type of stuff, like tourism, resource utilization, data, or plantation, mobility, something like that. What is your idea? What is moon business industry?
I think as iSpace, the resource is moon resources will be the economy. However, I think the second day of this event, I kind of realized when you think someone will be standing on the moon, maybe you will see different vision. So what I think is you have to have like a crystal clear image where you are. I mean, whenever human standing on the moon, then maybe you'll see, oh, I need a camera to take a picture. Then you have to ask the camera maker to use the camera on the moon. So I think my point is, just imagine, please imagine you are standing on the moon right now, and what do you see? That's the economy, I think.
So, so yesterday I presented the idea of Dear Doge. So obviously we are interested in building financial system in space that includes financial system for the moon. So that's one thing. But from Dora Hacks, our community's perspective, we care about open innovation platform. So SpaceX is one. I believe iSpace is one. So when they build the infrastructures, we hope like more people can think about what they can develop more use cases on top of these open platform technologies, so that there will be endless possibilities that you can build on a new planet. That's the most exciting part.
For moon economy, there, as Mrs. said, there are several, I think, sectors. Like for example, like DARPA Luna 10 also mentioned there for several key factors, logistics, and also like telecommunication, power, etc. I think all of these like essentials will probably come first. So some of them doesn't really require human interaction, but probably mid 2030 or so, there are gonna be definitely a need for human to get involved to do some complicated works, especially something to do with science. For example, there's some smart people needed on lunar surface in order to solve some of the difficult questions, because couldn't be automated. I mean, it's specialists up there, and people have to think there. I think that's coming probably in 10 years or so. And in order to do so, we have to train more efficiently. That's where I think Blue is coming.
So, in my opinion, for the moon economy, first we need to find the values for the Earth humans, because that the economy is always surrounded, or always surrounds the, how can I say, humans' value. So then, from the viewpoint of the value, I think that at first, how can I say, they are more like I say, the entertainment or like tourism can be occurs. And then from the viewpoint that my companies, maybe for tourism or maybe the safety or the navigation is important. Then it requires many companies who make sure the safety, such as the communication satellite or the navigation satellites, can be occurs. So it can be the more larger, the economy can be more larger. This is my opinion.
Right. As the terrestrial, the industrial automation company, we see the opportunity about the ISRU as the moon economy. And we start from the water extraction and to divide it into the hydrogen and oxygen. For the hydrogen for the energy source and also oxygen for the human habitation. This is a start. But then advance into the more material production, like material for the base and the habitation, etc., etc. So then the question is who could be the end users? So initial users, the public is the space agency. And also I have hope that a private initial customer can be tourism, because I want to see the moon, and also I want to see the Earth from the moon. So many people had the same opinion. So I like this could happen as soon as possible.
Yeah, call me a dreamer, but for me, the return on investment is not economy. I think that ISS was an awesome program because it managed to get international cooperation, and diplomacy was one of the main revenues from ISS. And I think the same could be applied for the moon. So what we are doing is something that goes far beyond money, and it's following the quest of the moon is very important for humanity for many aspects. So let me think about this in this way. Not so much the economy, which of course is giving us the money. But governments and agencies, I think that they should continue telling the people how important this is, regardless of how fast we can get the return on investment. And yeah, it's through taxpayers' money, but it's worth it.
Thank you. And to mention marine economy, honestly, I'm not sure there is a strong reason or benefit to develop marine economy. But I think there is a strong benefit to process to develop marine economy. Like we can gain some technologies like circular economy or zero emission technologies or like communication or navigation technologies. These technologies could be reach more high level by developing new economy, I think, and which will enlighten our Earth's life. So this is a strong reason to develop new economy and its benefit, I think.
So we have additional time. So last message to the audience from your experience of your entrepreneurship activities aiming to economic development.
So one message to your audience?
Yes,
okay.
last message.
Last message from MySpace. Never quit the Lunar Quest.
My message, build more products and participate in more hackathons.
All right. So from Blue Abyss, we actually started some of the astronaut selection and training service in the UK. So if you're interested in starting training, just let me know. I'm here.
So for my message, yeah, we think that the connection is most important for business. So like, yeah, connecting with the iSpace or the university students. So like the human resource is also important for future businesses. So yeah, if please say hello to me or please contact with us that even though the business is directly not connected with us, the connection can be make the economy. So I think that, yeah, this is most important part.
Right, my last message is, let's enjoy challenges and together. Thank you.
I would like to use a word, the word team. That's what has brought to me in life the most successful experiences. And yeah, as in my presentation we were saying, never fly alone. Thank you.
Thank you. And youth are empowered strongly when they figure out some world of technologies or some future. So please share your experience and your point of view to your future partners.
Thank you very much. And now is the time if you have some questions and opinions from floor. No? No questions?
Amazing. We want all to work with you. That's
nice.
Yes. So let's build also not beyond economy. Let's build the society on Earth and the moon. Yes.
So it's okay. So we have discussed about the economic side of the lunar development. And last of all, I would like to say entrepreneurship that all of your panelists you have is one of the most important things to create and broaden the lunar market, sustainable and scalably. Thank you very much.
Picture with like that? Yeah, right. Or we can do together. Or next time.
Test, test. We're gonna reconvene for the closing session in just 5 minutes. So because we want to go ahead and wrap up at a reasonable time because the museum is going to throw us out. So we cannot be late. So 5 minutes, actually 4 minutes and 45 seconds. And then we will start.
Thank you. Okay.
May I see the slides?
Yes. Just only two.
Remind one more time.
Yes, yes, yes. 稲谷先生、すみません、そこ頭をお願いしていいですか、すみません。Sorry. So we need your help. Accommodation survey. So yes, half of you already answered the enquete. So another half of you, please make sure to access. So please access to this QR code now and now. So and please input your information. You can answer 1 minute, only 1 minute. Please, your help.
Where is it?
If you have not answered the accommodation survey, please answer now. Answer it now. So you can access from this QR code. Please, we need your help. And I have one announcement. So after the last session, we must to go out this building in 15 minutes. So please check your bags and luggage. So don't leave your baggage and luggage. Please. So if you leave your baggage, so you can't return to this building. So until tomorrow's morning.アルバイトの学生さん、ちょっと椅子片付けてもらっていいでしょうか。 アルバイトの学生さん、椅子お願いします。
We are ready to get started with the closing session. Okay, if we could please sit down and get started. Gentlemen, ladies. The time has come. So, what's the matter?
Please keep the end time. So
I'm trying, but you're touching. Why are you talking to me?
Sorry.
You are taking the time.
Yes.
Sit.
Yes.
Okay. Okay. I think it's been an outstanding workshop and symposium. We've had a series of truly excellent plenary sessions over the last 2 days, not to mention a host of breakout sessions covering transportation, materials, construction, life support, the near term, the far term, the middle term, pretty much everything you could imagine concerning the moon. During the last 2 days, we have talked about it. Now we are wrapping up, and just to show you some statistics, we had 189 registrations, including the many sponsors, and 165 people who were here with us in Karashki. We had some 30 participants per breakout session and 85 presentations, 2 panel discussions just this afternoon. If you are you were one of the presenters and you have not yet provided your slides to Inatani Sensei and to Miura-san or to me, please do so that we can create a really nice product from this event and create a legacy going forward. I think this is the only one, okay? So, next, we're going to talk a little bit about tomorrow and the next day, and in particular concerning the logistics, because I want to remind you, our meeting is now finishing in Kurashiki, and we are now going to move tomorrow to Tottori. So, do you want to speak to the logistics? Please.
Thank you. So let me make confirmation about the logistics. Just wait.
But please hurry up.
Yes. So you can access to the information for logistics from this link of the top page of Symposium website. So bus information. So then you can find the timetable. So please check the latest timetable. So it may be changed, possibly may be changed. So please confirm the latest timetable. And so you can choose the two boarding area. So one is Kurashiki City bus parking area. That is near here. So just opposite side of Kurashiki International Hotel across the road. So there is Kurashiki City bus parking. And second option is Kurashiki Station North Exit bus parking. So just out of Kurashiki Station, North Exit. So North Exit is the second floor. In Japanese way, second floor. In the European way, the first floor. So you should step down, and you can find the bus parking in the ground floor. So please check the parking area, and please come to the parking area on time. Please on time. Yes, and you can, one more time, so you can find the information. So please confirm it.
This is the conference website.
Yes, yes. This is conference website. You can find the information from this page. So please confirm it. Thank you.
Okay. And next, we will have a brief presentation on the Tottori event, which is coming up on Sunday.
Thank you. Thank you, John. And I would like to appreciate all the panelists, and including the chairperson, John. You are the excellent coordinating everything. That discussion was very fruitful. And Inatani Sensei, a very, very nice session coordinating. And also Mr. Cross, and also, one more lady. I forget the name.
Misuzu.
Yeah, Misuzu. sorry about that. But actually, you are already satisfied the discussion today and the presentation. It was excellent. However, we have more than that. So, which means we will discuss about the possible ecosystem on the lunar surface. The advantage, and also this is our concept vehicle, which is a rotating centrifugal train concept, which maintains the 1D gravity when it's moving. Of course, this is a concept. But we are reaching now in Kurashiki. Kurashiki is very, very nice, traditional, and industrial city. So you have already enjoyed, but you will enjoy tomorrow. However, what is Tottori? Tottori is actually based on the lunar side. Of course, first we arrive to Kurashiki, we will enjoy Kurashiki one more day by two outreach events, which you will choose. I don't know, but you have here in discussion with astronauts, and also there is Okayama University. There are big also outreach. So please choose one. However, then we will move to Tottori. And this is Arid Research Center. So we will discuss about the future of the moon in the Tottori. What is the advantage of Tottori? is a site we call, it's a Tottori Sand Dune. Tottori Sakyu is one of the most famous place. It's not the desert, but it's a sand dune. It's the biggest sand dune in Japan. And this was built together with JAXA and Tottori University, one of the closer area, and exclusively tuned for the lunar surface analog. And this is also used by the private company. And this is also the amusement, digital augmented reality, which is as if you are standing on the surface of the moon, and you can have like imitating astronaut experience. The gravity is 1G, however, but you can enjoy. And this is a part of the venue of the Tottori University. What is this? This is a dome structure, and we will discuss a session about the core biome. It's one of the first topics that we are proposing. But we need to move to the different planet, not only the human being. We have to bring the ecosystem into it. However, bringing ecosystem costs too much money and too much effort. And you have to comprehend the system of the ecosystem. Ecosystem is not beyond the integrated system. It is nature, and nature behaves completely different what we think. And that kind of experience will be discussed together with Tottori University scientists and also scientists from University of Arizona. John Adams, he's actually, he was supposed to come here. However, he will be discussing from the COP28. He's joining the COP28, but he will give a talk. And also, we have an outreach talk, but this is Japanese. Japanese, please join outreach session like Mori-san that we talked to get today, and Ono-san, who is a gold sponsor and the Kajima Corporation person. And then we have Inami-san and also Cosmo Girls. And then, is this the end? Oh, that was the end. I'm sorry. So please don't forget to go to Tottori because you will miss a big if you don't go. Okay, thank you.
Thank you very much. And I think now we are ready. Not yet. Wait. Are you waiting? Don't, then why are you touching? Wait. No, don't go away. Don't go away, but don't touch. Okay, so now we are coming to the last few moments of this 7th Global Moon Village Association International Workshop and Symposium. And the time has come to announce where the meeting will be next year. So we of course, we are a movable feast. The very first workshop and symposium was in Europe at the International Space University campus in Strasbourg. 2018, we moved to Los Angeles. 2019, we moved to Japan. 2020, COVID. 2021, still virtual in 2020, virtual in 2021. Last year, Los Angeles. This year, back in Japan. And from a couple of excellent proposals for 2024, we have selected by a unanimous vote Luxembourg, with the support of the Luxembourg Space Agency. And so, if I could please ask Bob Lamboret to come up, and now the video. Okay. See, he was going to bring it up before I even had a chance to make the announcement. Please, and congratulations.
Thank you.
This is going to be a great meeting.
Yes, thank you very much. Of course, we are very honored to organize this event next year in Luxembourg. We thank you for the trust you put in us in organizing such a great event. I have a few slides giving you a flavor of what we actually proposed to the Moon Village Association, just to get some, how to say?
Now.
Yeah. Yes, so our proposal was to have a global space week in Luxembourg in December. So we propose to host the Moon Village workshop, and together also at the same time the New Space Europe event that we've been organizing for a few years now. And we're also in discussion with the European Space Agency to host another event on exploration during the same week in Luxembourg. So the tentative dates, all of this will be confirmed in the coming weeks and months. For the moment, we plan. We are in contact with the venue to have it on the 2nd to 4th of December in Luxembourg. And then yes. So for those who don't know Luxembourg, where it is, Luxembourg is in the city of in the center of Europe, around France, Germany, Belgium. Very easy to get there. We have no international flights, but you can fly through London, Paris, Frankfurt, Munich, Zurich, so on. So you have many connecting flights. Just quickly, so the venue will be located in the city center. There's a new conference center in the very heart of Luxembourg City, close somewhere between the new area on Kirchberg and the old city. So it's a very beautiful center, conference center. That's where you have the European Commission have their plenary sessions. And I think, yes, so that's so there you see when the European Commission comes over, probably will look a bit different when we organize the workshop. But yes, it's very nice place to host such events. We are looking very much forward to welcoming you to Luxembourg. We hope it will be as interesting, or we are sure it will be as interesting as here in Kurashiki. And yes, thank you very much.
So if we could do a photo, please, in the Tani Sensei, 2023. We passed the torch. No. But just shake hands. So,
next year.
Please, to next year. Okay.
Thank you.
Congratulations again.
Thank you.
Don't leave. Inatani Sensei, don't leave. I got you up here for a reason. Okay. So, Inatani Sensei, if you would like to say a few words, please.
I'm not representing the local organizing committee. Local organizing committee chair is Professor Eizo Nakamura, but he is now in Okayama for the preparation of the next day, tomorrow's outreach event. They are going to serve once again the ryugu salad down there. So, but anyway, thank you very much for your coming and for joining us with this Kurashiki part of the symposium. And the Totori part will be starting the day after tomorrow. And yes, on this occasion, our thanking to the Kurashiki people, or city mayors came. They are very good support from Kurashiki people and Kurashiki Chamber of Commerce and the mask people. And thanking to them, we have made this very good event on that. And the local organization committee, from our point of view, we are all 100% volunteer works. And I did a very little part, but Miura Sensei and some other guys, including the students, has made a very good job. So thanking to all of them. And yes, we are still going on tomorrow and the day after tomorrow. And see you again in Totori. Thank you very much indeed.
Please applause for the local organizing committee and everyone here in Kurashiki. Okay, With that, this really excellent first 2 days are officially concluded. I look forward to seeing you all in Totori in a couple of days or on the bus tomorrow. So thank you so much.
Okay.
これマイク。
あ、大丈夫。ありがとう。
はい、今モバイル自分のモバイルができました。
Don't leave your baggage and wallet and something. So be careful for leaving your baggage. 30 minutes later, so we will close this room and this building. Be careful of leaving baggage or wallets.